Hey Max, can you hear us? Hey,
Yes, I can hear you.
we cannot hear you. Should we?
Yeah.
You don't hear the people on the other side.
We're just a minute, Max. We're figuring out with the technicians. Thanks.
Okay. Max, Jorge, can you guys hear us? Can you not?
Yeah, I think so.
Okay, yeah. They're
We can hear
figuring
you.
out the sound.
Can you hear me now? I mean, I had a microphone issue also on my side.
Now we can hear
Yes,
you.
we can hear you.
Fantastic. Max, how are you? Super
Good.
busy, I guess.
Oh, yeah, I just finished my slides.
Okay. Thanks so much for being here today. So we'll start, I guess, in 5 minutes. So there's a keynote going on in the other rooms. So we'll just have the opening of the workshop, and then we'll give the word to you. You said that the seminar was pushed back a little bit.
Yeah, I'm good with time. So you need to remind me how much time I have.
Okay, so 50 minutes. That would be 1 hour. You can do like between 45 and 55, and then we'll do some like 10 minutes of questions.
Perfect. I think, yeah, that matches well. 45 is probably good.
Okay, so we can remind you around, when you have spent 40 minutes, and then that's gonna mean like 5 or 10 more minutes. But take it easy. There's no rush. Right? Thanks so much.
Okay, right, but you wait.
That's work history of the seminar. But it's an event, so it's good. We're supposed to give people tomorrow, so that is another today. Okay. But people will go to YouTube, right? So there's no way you can see. Can we do? And having 3. Are you going to read the entire marks to you?
No. Summarize it a lot.
I'll just say that these are pioneer and different systems. First.
Max, is it okay for you? We wait 5 more minutes before we start. Okay.
Yeah, I'm flexible, and I have until 12:30, so that's no problem.
Okay, then we'll wait a bit longer for give people a chance to arrive. Good morning, everyone. Welcome to the second ACM NanoCoCoA workshop, co-located with ACM SenSys. So my name is Jeroen van May. I'm one of the co-organizers together with Sergi Abadal, Philippe Lemich, and Chong Han. Welcome everyone here locally, people watching on YouTube and people in Zoom. So yeah, the basic idea behind NanoCoCoA started with nanotechnology. Nanotechnology is a key ingredient for this workshop, and so it continues to revolutionize a wide range of fields by paving the way towards sub-micrometer scale devices, so a few hundred nanometers, and this allows us to control materials on an unprecedented scale. And this is expected to give rise to a wide range of nano devices that have embedded sensing, actuation, data processing, storage, and communication capabilities, which will then open the horizon to groundbreaking applications like ingestibles or implantable devices for in-body healthcare, devices to control robotic materials, performing on-chip communication wirelessly, and software-defined metamaterials. So the key objective of this workshop is to bring together experts in all of these different areas. So experts on nanoscale computing, nanocommunications and networking, and these emerging applications. And I think today with the program we have people from all these different areas. We have presentations on computing and communications, presentations on different applications in this field. We have a very exciting program with starting with the keynote by Professor Max Lemme, an invited talk by Nick van Helleputte, and finally 2 technical sessions and 1 work in progress session. So in the workshop, we received 15 submissions, 12 regular papers, 3 work in progress papers, with in total 36 different authors, 22 affiliations from 11 different countries all over the world. We accepted 7 regular papers and 3 work in progress papers from 27 different authors at 16 different institutions. Every paper was rigorously reviewed by at least 3 reviewers from our technical program committee. And we'll start today's program, as I said, with a keynote by Professor Max Lemme from RWTH Aachen University and AMO. So Professor Lemme is a full professor at RWTH Aachen and also the scientific director of AMO, which is a nanotechnology company also based in Aachen, Germany. He's also the co-founder of Black Semiconductor, and he obtained his PhD at RWTH Aachen in 2004. He has worked in the field of nano CMOS devices and has performed pioneering research towards top-gated graphene MOSFETs, graphene-based non-volatile memory, vertical graphene hot electron transistors, and much, much more. He has received several awards, such as the NanoFutur Young Researcher Award in 2006, the Linen Research Fellowship in 2007, and he also received 2 prestigious ERC grants, a starting grant in 2012 and a proof of concept grant recently in 2018 to work on graphene technology. We are very excited to have him here. He's a top researcher in the field of nanotechnology, and his talk today will be about 2-dimensional materials as enablers for autonomous sensor systems. So Professor Lemme, I leave the floor to you. Feel free to share your screen and start your keynote.
Thank you very much for your kind introduction. Let's see if this screen sharing will work. This will stop your screen sharing as it's telling me. Very good. Okay, I actually put on the same suit I had on that picture you showed of me. So by accident, I have more than 1 suit. But well, thank you for the kind introduction. I'm excited to be there, even though I would be more excited if I could be there in person. But looking at the corona infection numbers, you don't want Germans there at the moment, I guess. We should all be vaccinated. Anyway, I will try to talk today about the 2-dimensional materials as enablers of autonomous sensor systems. And as I will explain, that these materials are by nature nanomaterials because they have dimensions of less than a nanometer in one direction mostly, and that's usually the definition of a nanomaterial. So this is the outline of my talk. I will give an introduction of the materials and of AMO as well. I will talk about different kinds of sensors, mechanical sensors, detectors. I will talk about 2D electronics, and then I will introduce the 2D experimental pilot line, a European effort to bring forward 2D material technology. First of all, Aachen University is located right at the triangle of Germany, Belgium, and the Netherlands. So you see the picture of the building of AMO actually down there, and in the background, the hills, those hills back there are already Belgium, so it's really close. And I'm the chair of electronic devices, and this will also be the center of my talk. AMO, as you mentioned, is a company located on campus. We are a non-profit, so you could also consider us an institute, a research institute or research foundry. We have this 400 square meter clean room. We're currently about 80 staff members in about 40 R&D projects. And as a baseline, we have a silicon technology, but we are strong in making nanostructures and integrating new materials into that silicon technology base. We target different applications. More recently, quantum technologies, neuromorphic computing have been added to the mix. And our mission is to enable technology transfer. So we do that with a lot of partners in these funded research projects or through startups like Black Semiconductor, which we founded a couple of years ago. Now, the talk today is about wearable or autonomous sensor systems. And I just added this slide a minute ago, literally, because I saw that in your logo, you have this picture of a person. And this really summarizes the components that I would like to speak about today and that we need to make autonomous sensor systems. And actually, the next slide summarizes this in, let's say, more in words than in pictures. What we need is we need sensors, we need RF electronics or electronics, we need ideally flexible electronics, and we need wafer scale processing in order to bring this forward. And you see down there the list of projects that contributed to work in this field. And actually today I will speak about mainly the green part here, the sensors, the RF electronics and integrated circuits, the wafer scale processing, and then I will touch slightly on the flexible electronics and Hall sensors. And well, coming back to the projects, Sergi Abadal, one of the co-organizers, is also the coordinator of the Whiplash project that you see here on the left-hand side. And thank you to Sergi for leading this wonderful project. Yeah, you also see some of these names are not in nice logos. They are just plain type. Those are the German Research Foundation projects, because the German Research Foundation doesn't care about logos. They care more about the research. Not saying Europe doesn't care about research, but there we have to make logos. Anyway, why 2D materials? This is the question I asked myself. Why would 2D materials be so good for autonomous sensor systems? Or if you could leave out the terms autonomous or sensor, why would 2D materials be interesting for systems? And we tried to answer that in this graph here. That's from a recent paper or comment paper. Let me try to use my laser pointer here. So what you see here is the time axis, and we call it performance. So it's kind of fuzzy what this is, but when you see on the left-hand side is the Moore's law, basically, where we go for transistor scaling, and this drives performance and cost in opposite directions. And so we all know this was the area of Moore's law, and it will continue. But if we can integrate materials in the future that help us continue that, 2D materials are very good candidates. If we talk about the future of electronics, if you look at the roadmaps that are out there, then stacked nanosheet or nanowire transistors are one of the candidates that could drive Moore's law towards its, well, ultimate limit. And 2D materials are ideal to 2D nanosheet transistors. So probably they can play a role there if we continue on the scaling. But you see also these other 4 fingers going up here in the more photonic integrated circuits, neuromorphic computing, or quantum technology area. And here, I believe that 2D materials can make a big difference because we can integrate them in the back end of the line. And this is what you see in this center image, the front end of the line where the high performance transistors are, but then there's the back end of the line. And if we can add functionality to the back end of the line, sort of adding an X to CMOS, then we have a hybrid integration. And I'm convinced that 2D materials are probably one of the best materials to try and do that because they have all these different functionalities. Taking a step back, looking at graphene. Why is it a nanomaterial? What is graphene? Well, it's a single atomic sheet of carbon atoms that are strongly covalently bonded in this hexagonal lattice here. So this is a ball and stick model of what graphene looks like. You can actually see that with a transmission electron microscope or with a scanning tunneling microscope. You can make that visible. And there are some parameters here, lattice constants, thickness. And if you look at a single atom here, what you see is that 3 of the electrons in the outer shell take part in making this a strong lattice, but the 4th one is not so much involved in that. It kind of sticks out on the surface of the graphene. And this is the atomic structure and what it looks like, but what this all means is that essentially graphene is the thinnest material we know. Because it's so thin, it's highly flexible. So flexible electronics are possible with graphene. It's the toughest material that we know because carbon atoms are so strongly bonded. It's highly conductive because we have this 4th electron, this pi electron, as a cloud of a sea of electrons on the surface that make it very conductive. And I will talk about that later. It's a broadband light absorber. But it doesn't stop there. 2D materials have been expanded tremendously over the last 10 years, roughly. We know now a lot of materials that are semiconductors. Graphene is not a semiconductor, it's a semi-metal, but we have semiconducting 2D materials, and those are the candidates for these nanosheet transistors. For example, here, the ball and stick model of molybdenum disulfide, where we have a transition metal and a dichalcogenide combined here. That's why they're called TMDs, or transition metal dichalcogenides. This has a band gap of 1.8 electron volts in its single single layer form. And we can also think of insulators like boron nitride. Boron nitride looks like graphene, except you replace the A and B lattice atoms with boron and nitrogen, respectively. So we now have this whole functionality with all kinds of different semiconductors, insulators, semi-metal, magnetic materials. Basically, if we can control these materials and even combine them, it's like a dream come true for material scientists because we can design and engineer materials for the purpose that we want them to be used in. We are still far from realizing that, especially on a large scale, but at the lab scale, we can already do this today. So this is a wonderful opportunity for the future. And in my research at AMO and at RWTH, what we try to do is we try to take the material and show some kind of functionality in a device. This could be MEMS devices, microelectromechanical systems, and NEMS. These are good sensors for many purposes, and I will speak a lot about that in the coming slides. Electronics, here we try to use high mobility, good conductivity of the material, and show new and flexible electronics. For optoelectronics, I will also show one example. And then, yes, we try to make this all non-flexible. And we always try to go towards the device. And then with some of our partners, we even try to go further towards these systems. And that's where we are in this talk today. So why 2D? Again, we have to ask that question. Well, the answer is at the device level, we have high performance. We outperform existing technologies at the device level. And we can hopefully one day integrate it in the back end of the line. This is coming back to my first introductory slide. Now, I will switch to the actual work that we've done, and I will go to 2D nano electromechanical sensors. And this work started many years ago probably when we first started with graphene work in 2006-07. My colleague Markus Morgenstern from the physics department is an STM specialist, and he was very interested in getting graphene early on, and we were able to provide that material on silicon oxide. And he looked at it first with an STM, and what you see here are two different surfaces. One is a surface on the left-hand side of silicon dioxide, and on the right-hand side, it's the same substrate, but covered with graphene. And what he found was these corrugations on the surface of the graphene. And actually that is one of the reasons why the material is stable, because if it were completely flat, it would probably not be easy to stay that way, and it would crumble up. And that's why people for a long time didn't believe that a 2D material could exist in reality. But we have these corrugations, and what this means, the difference in these roughnesses here, is that there are small membranes that are nanomembranes on the surface of this material, and they occur naturally. And Markus Morgenstern didn't stop there. So this was just the observation of the nanomembranes, but then his group did great work with their STM tip, and they found some of these nanomembranes that are just 5 nanometers in diameter. And he used the STM tip to actuate them. So this is the same spot. This is actually a picture of the graphene taken with the STM, and you see the hexagonal lattice here. So each black dot is just the center of these 6 carbon atoms that I showed before. So this is a real picture of graphene. And he found these nanomembranes, and you see, as a function of the distance of the tip to the surface, you can see that this membrane either is concave or convex. So he can move this membrane up and down. And then they did some calculations with the clamped membrane theory and molecular dynamics, and they both calculations ended up with a resonant frequency of that membrane of about 400 gigahertz. So the ultimately small membrane here of 5 nanometers could have a resonance frequency of hundreds of gigahertz with extremely high Q factors at low temperatures. And if one could make such a membrane on purpose, it could be used as a mass detector even for a single hydrogen atom, because that is the sensitivity that such a small membrane with the low mass would have. And here the thinness of the graphene comes in, because it's only possible because the material is only an atomic layer thin. Of course, these are small membranes, and hydrogen atoms are hard to detect. So a few years later, actually 10 years ago, when I was in Sweden at KTH, we started thinking about making pressure sensors. And the idea here is that if you strain graphene, you induce a band gap, so it changes the electronic structure of the material. Now, in a realistic device, we cannot achieve things like 22% strain, even though graphene is strong enough to hold up 22% or 20% strain. It's difficult to achieve that much in an integrated device. And the idea for the device, you can see here in the schematic, we made a hole in a surface, and then we cover that hole with graphene. And the graphene seals the membrane pretty well. And then if we change the pressure on the outside, we kind of bulge this nanomembrane up and down, which strains the membrane. And because we have these gold contacts here, we can measure the change in resistance across this device as a function of the pressure. So while we do not get the 20% strain, even small strain will affect the density of states, the mobility, the resistance. So we can measure this directly with our needles and our wire bonds. And here's the result. It took a while for the student Andy Smith. He's now an associate professor at Chalmers University. But anyway, so you see with the membrane here, we have a clear signal where when the pressure changes, we get a difference in the voltage across this device. So this is clearly the piezoresistive pressure sensing. And if we don't have a membrane, here's the reference device, we don't get a signal. It's noise, but it's flat. And here's the comparison to a pressure sensor. The red line is a commercial pressure sensor. The black line is our graphene pressure sensor. So this was the proof that these devices actually work. And then we went in and did a few more experiments and calculations. And you see here the a real picture of this device. The red part is the graphene membrane. Then we have blue excess resistance and some yellow parallel resistances. So we can just treat it like a network of resistors. And he did a COMSOL model of the deflection. And so we extracted gauge factors of, let's say, 3 to 5 for this graphene material. The gauge factor is an expression of how much the resistance changes as a function of strain. And this gauge factor is actually not very high, but because graphene is a semi-metal, this is to be expected. Nevertheless, because it's so thin, we can calculate the sensitivity, and the sensitivity has the thickness. This H here stands for thickness, as 1/h squared. So the sensitivity depends extremely on the thickness of the membrane, and we have the thinnest material on the planet. So that's as good as it gets. And if we compare then, scaled down to size, these graphene membranes are the most sensitive sensors for strain that we can think of compared to other existing technologies like silicon technologies for pressure sensing. So that's pretty good. But we also looked at another 2D material, and I like this material called platinum diselenide quite a lot. Why do we like it so much? Well, first of all, we can make this material at low temperatures, 400 degrees C. This is back-end of the line compatible, so we can directly go to the back-end of the line. It has a gauge factor of, well, it depends on the material, but it can have gauge factors, negative gauge factors that are very large, or rather large, 85 here. It's not extremely high, but still the thickness of the material is comparable to that of graphene. And so when we made pressure sensors of the same type with platinum diselenide, we saw that they outperform all these other technologies and even our own graphene devices. And we even have one case where this exceptional device is another more than order of magnitude better than even the best platinum diselenide. So here we combine material that has the thickness of a 2D material, or the thinness, and a high gauge factor because it's a different composition, a different material than graphene. And so this is a good example of how we can use 2D materials for specific purposes if we understand the materials well enough. So platinum diselenide is the better pressure sensor in this case. So my colleagues at KTH also went forward with an idea that we had way back. If we now have these membranes out of graphene and we attach a silicon-proof mass to it, can we make accelerometers? And of course, the idea started as a picture, and then this turned into a nice, rendered image now. And at the time, I was very skeptical that this could be done. So the time being 2014, 2015, so definitely way before this paper came out. And the student actually insisted on trying to do that, and I was very skeptical, but he pulled it off with a lot of hard work and effort. And Shuge Fan is now an assistant professor in China. So congratulations to Shuge, hard work pays off. Anyway, so the idea is that we can have the membrane and the transducer both made from graphene, and the silicon-proof mass can be really small because we can make these small membranes and have the high sensitivity. And here's another proof that this actually exists. So here you have an SEM image with the graphene, and in the center you see the proof mass, and there's an air gap in between. And if you put this in a shaker, this proof mass will then, due to inertia, cause strain on these membranes, and that can be measured. What we showed with this device is that we can reduce the silicon-proof mass by a factor of 1,000 compared to the state of the art. And we can reduce the footprint of this sensor by a factor of 100 compared to the state of the art. So this is, again, an example where graphene can make a difference in a device, and a decisive advantage it is. Now, during our work on the pressure sensors, we also saw in some early experiments that even without a membrane, so there's a membrane here, there's no membrane here, and the blue dots show the measurement results. Again, we're changing the pressure, measuring the resistance. So there is a trend, even if there's no cavity. It's much more noisy, but it's a clear trend if we do the averaging. So we had to figure out why on earth was there a signal if we didn't expect one from the piezoresistive sensing. And the answer took quite a while to get, but the answer is that there's humidity. If you change the pressure, humidity was entered into the chamber, and that humidity was also sensed by the graphene. So there was a cross sensing, and this is of course always a problem with sensors. You have to make sure that you're sensing what you think you are sensing and not something else. So Andy went back and actually did a lot of experiments. He built a new chamber, actually a humidity chamber, and figured out that, well, then he also added a humidity sensor to his original chamber. So now we have a voltage here, and we have a pressure here, and we also have the relative humidity, and you see that it all corresponds quite well. And he was able to measure with the vacuum chamber and humidity chamber everything from close to 0% relative humidity up to 90 something percent. And also what you see when you move the device from one chamber to another chamber, it continues to work, without a break here. So at the end of the day, this humidity sensing was also explained with a theoretical model and published in this nanoscale journal. And yeah, you see again for argon, nitrogen, oxygen, pure gases in the chamber, the sensor didn't really react. But as soon as air came in, and this clearly gave a strong signal, and it corresponds again to the humidity here. And he was able to show that you can also use it as a breath sensor and so on. So compared to the state of the art, this sensor actually shows a wide range of humidity where it can sense. There's a commercial device here. The response time is a factor of 10 faster than the commercial sensor, the recovery time as well. And well, when you compare sensitivity with these sensors, it's always difficult to kind of find a common ground. So we were a bit careful with comparing it there. So graphene is an excellent humidity sensor. This ends the part on nano electromechanical sensors, and I would move on to 2D photodetectors now. Why would we use 2D materials for photodetection? Well, in particular, graphene and also platinum diselenide for that matter, don't really have a band gap. And if you look at the commercial photodetectors like silicon and 3.5s here and other compound semiconductors, germanium, of course, the sensing capability depends on the electronic band gap. So silicon with its band gap of 1.17 eV will stop detecting light that's in the infrared range. The same for many other materials. And then others are not very good at the UV range, so they're not very broadband. They each have their own specific niche, one could say. And now some of these materials here are pretty hard to make. We can make them today. They're commercially available, but they're still somewhat expensive. So for example, infrared cameras really cost a lot of money. And well, graphene has a big advantage here because it's completely broadband. You can see on the left-hand side the band structure of graphene. It's with its semi-metallic nature, where the conduction band and the valence band just touch each other. They actually called it a little different, but anyway, that's how we can see them. And then we have sort of drawn in these colorful arrows, which mean that you can shine light of any color from UV to mid-IR onto this structure. And if the Fermi level is at the center, if the graphene is tuned to the right way, you basically can detect all of this. Same goes for platinum diselenide if you have the right kind of platinum diselenide. We can produce graphene, I'll come to that later. It has high conductivity. We can tune the material, the Fermi level, which means you can also block some of the light if you tune it far enough, so that it could be a modulator also. And it's flexible, we can integrate it. So it's really a wonderful material. It has low absolute absorption. That's maybe a downside. Of course, if you have a monoatomic layer, you shine light from the top, you absorb very little light. In fact, for graphene, it's 2.3% roughly across this whole range. But we can also make structures that don't worry so much about this low absolute absorption. And we're trying to use this a capability of infrared photo detection to make CO2 sensors. So I'm talking about photo detection, but now I'm talking about CO2, and I will explain that in a second. So why do we want to do that? And this is a slide from our partner SenSair in Sweden. Well, our brains are developed to work at a low ppm of CO2. We often have CO2 levels that are far above this 300 ppm, and I hope you have a window open in Coimbra, because otherwise you get tired and sleepy and you're bored by my talk then. So I wouldn't want that. So please open a window, because what you see here is one of the PI from Henrik Rødegaard, from the PI from SenSair, and as he was in his car, he had this CO2 sensor, and he started at this place over here in Sweden, started driving, and the yellow dots here mean that he was also tracking his progress with GPS. So for each data point here, he took a measure of CO2, and then after a few minutes in the car, you see that the CO2 levels get way above 1,000, 3,000, and that's why you get sleepy, And he always says it's very important if you're in the south, in particular, if you have an air conditioning in your car, you turn it on recirculation because it saves energy. Well, yes, it saves energy, but it also drives up the CO2 in your car. So be careful when you do that. In any case, the way CO2 works is, well, it has certain, or what we see here is basically the spectrum in the infrared range. And if you look at the different radiation, a lot of that gets absorbed by the atmosphere and by water. But we also see that, for example, carbon dioxide has certain high absorption peaks, and just by chance or maybe by nature, they happen to be sometimes in gaps. So for example, at 4.3 micron, you can detect carbon dioxide, but the sort of water will give you a window of opportunity because water does not absorb at 4.3 micron. And so you can have optical detection of carbon dioxide. And the way that's done today with sensors is you have an infrared light source, you have a big chamber with a gas inlet, and then the light, gets detected on the other side of your chamber. And then depending on the number of molecules of CO2 in here, more or less light gets detected on the detector side. But these systems are kind of big and clumsy, and they cost a certain amount of money. And if you could miniaturize this onto a chip, you would save a lot of money, and you could miniaturize it so you have a better size, better cost. And here for the detector, we were thinking we could use graphene. And then we brought together the expertise of KTH. So they make these specific waveguides. So this brings the light onto a chip. And you see here, this is a spiral waveguide that's quite, it's really long. It's, it could be centimeters long. And it guides the infrared light inside. And the interesting part is that they designed it so awkwardly and so flat so that part of the light is outside the waveguide. So the light stays in the waveguide. At the same time, you have part of it on the outside. And this so-called evanescent field then, of course, sees the environment. And if you then have CO2 here and you have 4.3 microns of light inside the waveguide, well, then you start absorbing the light, and you sort of get less light at the other end of your waveguide. So essentially it brings what we had here as a big chamber onto your chip. And on the detector side, we at AMO had built integrated waveguide photodetectors with graphene. So you see a silicon waveguide here, looks a little different, but it's the same thing. And we can put graphene on top. And now the light that comes in gets absorbed by the graphene, and it's no longer perpendicular. So we can get 100% absorption in this. And in this project Ulysses, we have been looking at this, and we've actually also now started to do this with platinum diselenide. So there's a platinum diselenide waveguide integrated into silicon photonics, and with that we can detect infrared light. So now we can make these highly confined small sensors, and we're working on bringing this forward. And the idea is to ideally also detect multiple gases with a fingerprint type of sensor. And we have a follow-up project that's also started. It's called AEOLUS, and this AEOLUS project wants to use these miniaturized systems and bring them to the cloud and make networks out of them. And then this is more or less the topic of today's workshop, right? So we want to target different gases and enhance the sensitivity, and then have devices that can be, placed in cities to detect the air quality in cities, and then ideally to help, guide traffic, close down traffic, maybe allow just bicycles and things like that. So this brings me to the next part, electronics, because now we have the sensors and we now need to move and get the signals out. If we want to make autonomous systems, we need electronics. And here graphene has some advantages because it has high mobility. So it could be a really fast material. On the other hand, it also doesn't have a band gap. So a graphene transistor is not really what circuit designers like very much. I'm not going into detail, but it doesn't switch off basically. So you always have some off current. So instead of a transistor, at AMO we made diodes, and we call them metal insulator graphene diodes. And essentially what you have is you have a titanium, in our case, titanium electrode, then you have titanium oxide as an insulator, and you have graphene on the other side. Now, metal insulator metal diodes are well known. They are high frequency devices, and we replace one of the metal electrodes with graphene. And we do that because the band structure of graphene, the Fermi level in graphene is tunable, so we can sort of play around and optimize the band offset on one side. We can make it larger or smaller depending on the bias. And this leads to a clear diode behavior. So you see in red here, the current as a function of voltage. In linear scale, well, this looks like a diode to me. And in log scale, you see there is a current in one direction, in both directions, but it's much smaller in one direction. And we can bring this onto flexible substrates, and then we can measure this. It's quite difficult to do with the ground probes, but we measured this Q factor at 60 gigahertz. And so these diodes we know work at very high frequencies. This was actually the measurements were actually partly done by my colleague Renato Negra and his group at Aachen University. And well, then we looked at these diodes with some sort of benchmarking figures like asymmetry, nonlinearity, and responsivity. Again, I don't have time to go into detail, but these are typical figures of merit for these metal insulator metal or metal insulator graphene diodes. And when we compare that to the state of the art, we see that the currents are quite high that we can get with these diodes. The asymmetry is reasonably high, can get better with other methods. But then again, the nonlinearity and responsivity are high. So we really have a good mix of high performance indicators for these graphene diodes. Now, a diode is not a circuit. So again, Renato Negra assisted us, and also colleagues from UAB in Barcelona, to make power detectors. And for that, we also connected that with some outside circuitry, got an input signal and an output signal. There's a bias T, there's a low pass filter. Well, the top one is for demodulation, the bottom one is for power detector. And again, we could sort of show that these devices work as power detectors in this type of circuit at up to 50 gigahertz. So this was the first step towards circuits, but ideally one would like to bring this onto a chip. This is still done on a breadboard with discrete components. So for that, we need, of course, these components like capacitors, inductors, and resistors on chip. And so at AMO, we developed this complete MMIC process, which has several dielectric layers. It has several metallic layers, and graphene can be introduced here at the diode level. It can also be introduced at other levels later on, but this is where the graphene is. And then we can make all of these components in this MMIC process. And so Renato Negra, again, colleague at Aachen University, also a partner in the Whiplash project, he took the diode characteristics and turned it into circuits and used the MMIC and the sort of specs from our MMIC process to start designing away. And he did. And we built this then, and then he measured this again. And so there are several examples here, and there are circuit experts in the audience probably who know much more about this than I do. So I will not go into details to embarrass myself, or not to. And what you see here is a 6-port receiver with 4 graphene diodes. These are the red circles here. You see the inductors and the other components that we built. This is on quartz, but it can also be built on flexible substrates. Well, then there was a double balanced up conversion mixer, a V-band power detector, a 3-stage distributed power detector. And there are many more examples for circuits that have been built and designed and built in the meantime. And in fact, we're just writing, led by Renato's group, a review paper that hopefully will appear early next year on the state of the art in this field. So now we have the RF circuits, and some of them have been used to transmit video signals and so on. So now we have also the opportunity to include in our systems the wireless communication. So the next topic we're addressing currently in Aachen, we're trying to use 2D materials also to build new neuromorphic hardware for artificial intelligence applications. And I could talk a long time why we need neuromorphic hardware for AI applications, but I try to keep it short. The main reason is that, well, yes, we can do a lot of AI at the moment. Maybe it's AI, maybe it's just machine learning. Anyway, it makes a big difference in many applications. And we use conventional hardware, or the people who do this, like GPUs, that are very good at solving or doing vector matrix multiplication, which is at the heart of this, but they're not very power efficient. So you need a lot of electric power to do that. And I always have 2 examples. One example is if you wanted to have an autonomous vehicle today using conventional GPU hardware, you would need as much energy, electrical energy, to think than to drive. So electric cars will use about half of their energy for being autonomous, and the other half they can use for propelling the car. So that is not a sustainable solution. And now the cloud may be an option, but well, first of all, would you trust your car if it runs on 5 or 6G networks? 5G is actually not fast enough, so it has to be 6G. Today I wouldn't, to be honest. And so that's an issue. We need to bring this down. And even if we had 6G and this was used, each car would create about 20 terabytes of data per day. And already today, data centers are using too much energy. In Frankfurt alone, the data centers use more energy than the airport. And this is before the pandemic. So not sustainable. We need new hardware. And ideally, we would like to have hardware that is inspired by the brain, where computing and especially pattern recognition, which is also at the heart of machine learning, is extremely power efficient. It's not fast, but it's 20 watts per brain. So it's actually much, much better than conventional compute hardware. One of the problems is, of course, the von Neumann bottleneck, where you have computing on one hand and storage on the other, memory on the other. So one of the ways forward is to merge memory and processing, and then we can use memoristic devices for that. These are transistors or devices that actually store their state. So it's a non-volatile memoristic device. And then we can use these as non-volatile memory. We can use these potentially as computing and memory elements. And we can also build artificial synapses from this. And I put these 2 projects, NeuroTech and NeuroSys, here, because these are 2 large projects that will start in the Aachen region very soon. Actually, NeuroTech was started Monday, 2 days ago. And we're hoping to start this NeuroSys project in January also. Why 2D materials? This is always the question one has to ask. Of course, we can do a lot of these things with resistive RAM and phase change materials. So there are existing technologies much more mature than 2D materials. But if we want to go towards low operating power, some of these materials need higher currents, higher voltages than we would like to give them. And 2D materials being so thin, they bring an opportunity to lower the operating power. And what we need in such a system is really two different things. We need non-volatile memristors that can be the synapses if you want, and we need threshold memristors that are the neurons. And there's a classification of resistive switching in this nice review paper by Mario Lanza and co-authors. And in one case, you go through this hysteresis curve. So you need to sort of go back to reprogram it. This is a non-volatile resistive switching. And then you also have threshold memristors that could be the neurons, where if you go up in the voltage, it changes its resistive state. Then as you go down, it comes back to its original resistive state. So these two types of devices exist in parallel, and they're needed. And we've shown that you can do, for example, one with molybdenum disulfide, and you can do another one with hexagonal boron nitride. And this is a field where 2D materials can eventually also become important cornerstones. I mentioned this NeurosYS project. I just wanted to give you more of a political slide. It's a regional cluster. That's what the BMBF wants to set up. So we have Aachen University, AMO, and the Research Center Jülich. We have local companies. Some of them are startups. And we have also innovation drivers that help us to make something out of this. But we also have a large advisory board, and because it's a national project, most of these are German companies like Bosch, Siemens, BMW, Infineon, Elmos, and so on. We also have the European startup from the European processor initiative called Cyperl. They are in France and in Düsseldorf, and so on. So we have this advisory board where we try to also involve these large players, and we get a lot of positive feedback already from them today. So this is really a topic, I think, that is going to be vibrant for the next 10 years or so. Now, finally, my last slides. I hope I'm not way over time. Where are the challenges? Why aren't we seeing these wonderful 2D materials in any products today? And the answer is clearly that the technology readiness level or the manufacturing readiness level is not where it could be. And this is one example, sort of a zoom in of what I showed earlier. We have a CMOS here, and we want to include graphene or 2D materials. And for that, we have to solve some problems. The first one is the growth. Okay, we can grow already on wafer scale materials. The company from Aachen called Extron has reactors that you can buy, and you can grow 300 millimeter worth of graphene, molybdenum disulfide, and other materials on metallic substrates, on sapphire. But these films have defects, they have wrinkles, they have contaminants, they are not necessarily monolayered, they're regions with single layers and double layers and so on. So the growth is there, but it needs to be perfected. Then a lot of these processes need temperatures up to 1000 degrees. So people who are working on CMOS, they understand that you cannot do that if you've already built your CMOS underneath. So because diffusion, as you see here, P and N type diffusion, will just continue at this temperature, destroying your CMOS circuit. So you need to have transfer processes where you take a monoatomic film from one substrate and put it on another substrate. You can imagine that that is not easy. Okay, graphene is the toughest material, but it's still, you can still easily tear it because it's so thin. So we need manufacturable transfer processes. We need electrical contacting. So with graphene, this problem is solved, but with semiconducting 2D materials, the electrical contact is often too high. So you have a device that is mainly dominated by the contact and not by the material itself. We need etching processes. If you remove monoatomic layers on top of other monoatomic layers, you need to have atomic control. The same goes for encapsulation. As soon as you put something on top of the material, it changes possibly its properties. Think of the humidity sensor. Yeah, it's a great humidity sensor, but it also means that anything you put on the surface will influence the device. So there has been a lot of papers dealing with this, with these sort of global issues and thinking about them. And Europe has fortunately started to fund a project called the 2D experimental pilot line from lab to fab. This was born out of the graphene flagship, and it's a small part of the flagship, yet sizable with 20 million funding. And it started a year ago. And the idea is that we want to establish a European ecosystem for 2D material integration and, make it compatible with the standards in the industry. All these little issues that I described on the previous slide are solved for conventional materials and semiconductor processing, but not for 2D materials. We need the tools to do it, machines, we need the chemistry to do it, the materials to do it, and this is also part of the 2D EPL, as it's called. We also want to already offer foundry services. So, there are many startups who have ideas, who have shown that something they can do would make a game changer if it could be commercialized. They need more professional access to large scale fabrication of devices and sensors. And so the 2D EPL wants to also establish this foundry service at an experimental level. That's why it's called experimental pilot line. But the ultimate goal, of course, is to achieve low volume production and transfer this to, let's say, the real industry. And the way it's set up is that we have tool manufacturers. Zeus is good at wafer bonding and transfer. Extron is good at growing. MRT is micro resist technology, is a chemical company that makes specific chemistry. We need that for all these processes. Oxford Instruments makes deposition tools for 2D materials, but also for the electrics, and etching tools for atomic layer etching. And Graphenia is a company that grows graphene, but also starts to become a foundry. Then we have 4 clean rooms at VTT, Finland, IMEC in Belgium, AMO, and IHP in Frankfurt, ODA in Germany, that develop the modules and the platforms to actually do something with these tools. And then we also will offer these multi-purpose wafer runs starting next year, where you can access with a low entry barrier, get chips with 2D material devices for your experiments and for your startups, for example. And these services then you can access through the Graphene flagship and sign up for it. We also want to transfer it eventually to the industry, and because it's European, to the European industry. So we established an industrial advisory board, and you see XFAB, AMS, NXP, Infineon, ST, Embareo, Nokia, Elmos, all of these European companies in the semiconductor field. And we have very good discussions with them. They follow closely the progress, and they're very excited to be on board of this EPL project. Coming back to the multi-purpose wafer runs. So initially we're at this red dot at the moment, this line here. We're currently developing that, and the first run will be by AMO. This will be, I will come back to that on the next slide. Then there will be a run by VTT, AMO, VTT, and eventually in the second pillar, this is all 200 millimeters. IMEC will, in the meantime, develop process modules that are more manufacturable than what we do, but it takes a longer time, and hence we wanted to be able to give you foundry access already early on, and which is what we're doing here. And yeah, just in a glimpse here, what we're doing: wafer scale growth, wafer scale transfer, and then we end up with wafer scale integration. So all that is there today. We just now need to sort of nail something down and make sure that these are the specs at which you can design. This is the process design kit. And here's the glimpse I promised on flexible electronics. We can also do that in flexible electronics. The specs are here that are being developed. The details are not important. The device will look like this, where we have a backgate and you have graphene and you have contacts, and it can be encapsulated or not. In February next year, we'll open the call. In June, there's a design freeze. And then in the fall, this multi-purpose wafer run will proceed so that towards the end of next year, we can make the delivery of the chips. So this brings me to the summary. Are 2D materials enablers of autonomous sensor systems? I tend to think yes, or I'm convinced that yes. I showed graphene sensors, membrane-based sensors with extremely high sensitivity and small footprint. I showed platinum diselenide, with high piezoresistive gauge factor, IR responsivity, and CMOS BOL compatible growth, which I think is a big selling point. I showed RF electronics with 2D materials from diodes to circuits. Then I showed how we feel that we want to take this to the next readiness level, manufacturing readiness level, with a 2D experimental pilot line. With that, I would like to thank the funding agencies, because this has been funded by many different projects, as it was also quite diverse, and collaborators from all over Europe. And thank you for your attention.
Thank you very much, Professor Lemme. So maybe first we have time for a couple of questions, and I'd like to remind the people following online that they can ask their questions on the Slack channel of the workshop, or they can raise their hands if they're in Zoom. But let me first see if there are any questions here in the from the live audience. Okay, then I see on Zoom, Jorge has a question, so go ahead and feel free.
Thank you very much. Can you hear me?
Yes, very well,
Yeah.
thank you.
Thank you very much for the slides. This really nice contact with the current technology and also for the future technology that we might get access. It seems that it will be sooner than later. I would like to ask, because you have mentioned it on the slides that this is also at some point you want to get this technology aligned with the current, let's say, standards. But I was thinking, are the current standard supporting this kind of technology? That is, this technology might boost in somehow the conception of new standards. I was imagining, for instance, these frequency bands 400 gigahertz, I think. But I don't know. I do not know any standard that cover this frequency range. Could be then this technology imply that new standard must be conceived or written? Thank you.
You mean now the standards for the communications?
For instance.
For example, yeah. So I mean, we're talking about different levels here. One thing, of course, is if we talk about the processing, there are also standards, of course, and there are discussions with the semiconductor industry, of course, on this. IMEC, of course, has all the big players, and I know that the 3 leading manufacturers in the world are interested in 2D materials. So definitely at that level, at the material level, this is part of it. The graphene flagship is part of these standardization committees also. For the communication, the 400 gigahertz was a mechanical resonator, so that's not for communication. That was more for sensing. But of course, the question, I mean, 6G is defined more or less, so we know where we have to go with our graphene RF electronics if we want to go for 6G. But you know, I think we need to demonstrate that it works technologically, and what the standards for communication will be developed, I think, independent of the material. Of course, if we can open up new corridors where conventional materials cannot go, I mean, this is future. But then, of course, automatically one needs to sit down and discuss with all those standardization committees.
I see. Thank you.
Looking at Philippe, if there are any questions on the online channels.
Professor Lemme, thank you for a very nice talk. There is a few questions. I'm going to read the first one. So based on your experience with graphene and other 2D materials for sensing, energy harvesting, and communications, how far do you think we are from a functional nanosensor mode that could be injected into the bloodstream, for example?
Okay, I mean, for the lab demonstration, we can already see some of these, flexible sensors based on 2D materials. My colleague Deji Akinwande has shown that they were sort of they had a sticker that they put on the forehead, and depending on the eye movement, the sticker was picking up signals of movement from the forehead and directing a drone. So I mean, okay, that's in a limited, confined space and a clearly defined task. Bloodstream, okay, there are many other aspects to be considered when we do that. Ethics is one of them, but the other thing is, of course, toxicity. And the graphene flagship is actually doing a lot of research towards toxicity of 2D materials. And of course, others are doing a lot of work on the standard, on the toxicity of nanomaterials in general. And one has to consider that. I mean, the current state of the art, to my best knowledge, is that these graphene and 2D materials are typically on a surface, and they're built into a system, and so they're not dangerous because, well, they're not, you know, nanoparticles floating around in your bloodstream. Of course, if you know, this needs to be clarified. So how far are we from that? Wow, probably at least 10 years, I would say, because that's not the first thing that will happen.
Okay, thank you. And there is one more question. How do you protect the nanomaterial-based components from the humidity and other external factors, especially in potential applications where the devices are on the wild? Do you think that that's possible, or we'll need to go for more protected applications where the sensor, for instance, is less threatened by external factors?
Well, that's always always an issue with sensors, and I first of all, I can say that we can, if we want to, we can encapsulate the material like shown here with this encapsulation layer, and we can get rid of the humidity effect. So we can do that if we want. On the other hand, if it's a sensor, so for a strain sensor embedded in something else, that's fine. If we have a sensor that is exposed to the surface, one always has this issue of cross sensitivity. But here, for example, the platinum diselenide, my colleague Georg Duisberg showed that platinum diselenide is very sensitive to N2O, much more than to other gases. And if we then look at different 2D materials, they have different sensitivity levels to different molecules, for example. So the dream of the electronic nose could be feasible because, well, then it becomes, you need a multi-sensor system, but because each one reacts differently to certain components, you can then use machine learning and fingerprinting, and you get your electronic nose. So I think one cannot avoid it completely, especially if you need the 2D material to be exposed. But one needs to work around and yeah, act like, be inspired by a dog's nose, essentially.
Thank you. And one last question for me. Yeah, in the talk you've talked about using graphene for sensing. We touched on using graphene for communication and for many other functionalities. So the question is, would it be preferable to continue with some traditional technologies, and what would be the functionalities for those traditional technologies, kind of?
You mean instead of doing the 2D materials, or?
Yeah, do you see some components, say, of a small device, of a nanoscale device, where traditional technologies would be better than graphene and related materials?
Oh, sure. I mean, if we think of flexible electronics, then the question is always, do you need the electronics itself to be really flexible, or can you use just a silicon chip and thin it down and put it somewhere in the corner? You know, if you want to make a smart textile, you just need a small chip somewhere and just some wires. So there's always that, and silicon is so strong, it usually tends to beat its competitors. But if we look at IR sensing, if you look at you know, this ultra low mass detection and so on, those are the things that you cannot access with conventional technologies, and that's where these 2D materials can make a difference. And the same, you know, so I think one always has to be clear on what one wants to achieve. I didn't show another example. If you functionalize graphene with nanodots, and this is something Frank Coppens and his co-workers have pioneered, you can put infrared sensitive nanodots on graphene, and then you can make a really responsive, highly responsive infrared photodetector that outperforms existing technologies, and at a price that is very, very competitive towards these 3.5 techniques, which are expensive. So, you know, they're developing now a camera, infrared camera, that will be eventually much cheaper than existing infrared cameras so that it could become a commodity. Nowadays, you have to pay hundreds of euros or even thousands to get a good IR camera. In the future, it could be in your phone. So, I don't know if we want that, but it will happen. So I think the advantages are specific for each application. One always has to think from both sides. You cannot just think from the material.
Okay, thank you very much, Professor Lamme, for the very interesting keynote and for answering the questions. So I think we'll wrap it up here, this first session. So we can still have a short coffee break of 15 minutes. And then we will meet again at 11:30 local time, so Portugal time. So thank you very much, and see you all in 15 minutes.
Thank you. Thank you for the invitation. Enjoy your coffee break. Bye-bye.
Thanks so much, Max.
Thank you. Yeah.
for the questions. It was an amazing keynote.
Hello, Jorge, I think you're here, right?
Yes, right. I'm here.
Yes. And then we have Daniel. Hello, Daniel. I don't see Hadil, but I think we have. We don't have a. We have a video for Hadil. So yeah, I think. So Philip, correct me if I'm wrong. So now, Jorge, whenever we start, I will just start with reading your bio. And in the meantime, you can share your screen with your slides, and then you can start whenever. We'll wait a couple more minutes because people are in the break. Coffee is there, so you cannot fight coffee.
Okay, then.
But yeah, that's pretty much it, right?
And then can you see the slides? Yeah, can you see the slides? Can you hear me? No.
Okay, so welcome back everyone after the coffee break. We're gonna start with the first technical session of the day in body nanocommunication and sensing. We will have three fantastic talks by Jorge Torres Gomez, Hadil Elayan, and Daniel Martins. So first one is gonna be Jorge with the paper, A Machine Learning Approach for Abnormality Detection in Blood Vessels via Mobile Nanosensors. So feel free to start sharing the screen when you want, and we can start with the presentation. Yeah. So before that, let me just give you a few words about Jorge. Jorge Torres Gomez is currently with the School of Electrical Engineering and Computer Science in TU Berlin. From 2008 to 2018, he lectured at the School of Telecommunications and Electronics in the Technological University Jose Antonio Echevarria in Cuba. He has been with the Department of Signal Theory and Communications in Universidad Carlos III de Madrid in Spain as a guest lecturer, and with the TU Chemnitz as a postdoc. He's on the Committee of the Educational and Professional Activities in the IEEE German Chapter Executive Committee, and his research interests include molecular communications, DSP, SDR, and education. So Jorge, whenever you want, please go ahead. Thanks.
Thank you very much. Can you hear me? No. Can you see the slides? Okay. Well, okay. Thank you very much for your welcome. Unfortunately,
Okay, please just wait a minute because we don't hear you and we don't see the presentation on the screen.
And can you hear me now?
Jorge, can you hear us?
Yes, I can hear you.
Can you speak now? I don't think we're here yet.
Yes, I can hear you.
Can you share the screen, Jorge, again? Okay, now we see it.
Can you hear me? Can
We
you
still
hear me
not
now?
hear you.
You cannot hear me.
Okay.
And now, can you hear me now? Can you hear
Yeah,
me
on
now?
Zoom you can, but here live we don't. So just a couple minutes
Yes.
until we solve this issue.
We had the same problem in the beginning, and then your colleague fixed it. I don't know what he did. Maybe we need to select the mode or. He tried to speak again.
Jorge, can you say something just in case? Right, okay.
Yes.
Now? Okay, good. Now
Okay.
we hear you?
Yeah, sorry.
Yes. Can you hear me then?
Yes.
Cool.
Okay,
Then I will
so
share the screen.
yeah, please share again. Sorry about that, everyone.
No, not a problem at all. This is happening typically in the very good events.
Yes.
Yeah,
Okay.
can you hear me now? Can you see the slides?
Yeah, it's all good. Thanks.
Okay, then thank you all for this warm invitation and warm welcome. Sorry for not being there. I couldn't be able to manage to do so, but for the next event, we are looking forward to be there in presence. We are presenting this work titled this machine learning approach. That is, we are conceiving a machine learning solution just to detect some abnormality inside the blood vessels by using some mobile nanosensors, more or less connected with the previous talk. And then the author, we are coming from 3 different institutions. This is we're in collaboration with the Michigan State University, at the USA, Lakeside Labs at Österreich, and then TU Berlin. From Michigan State University, this is Bige Dennis here. From Lakeside Labs, this is Jennifer. And then from TU Berlin, Anke, Ketki, me, and Professor Falco Dressler. Just to introduce the topic, this is mostly what is presented on the state of the art, that is for the human healthcare system. By using nanotechnology, we can target specific regions inside the body, and then to treat and also to sensor a specific tumor, for instance, and here exhibited in this figure, just by flowing nanosensors through the vessels. That is, they can be in somehow directed, just specifically there, and then to sense what is happening there, but also to deliver drugs there. For that, reported solution used to assume that we can have a nanobot or a nanosensor with all these capabilities, with a navigator, with an steering wheel, with some info to collect and also to deliver there, also with fuel and also with a propeller here. But the problem for the current state of the art is that mostly this is only in one path, that is from point A to point B, and we need really good external system just to guide this nanosensor specifically there. And this is really, really challenging. To our case, what we are considering is a system where we take care of the complete human body, and then we are conceiving such nanosensor here on the bottom, trying to detect some quorum sensing molecules released by some bacteria located at a wound on the skin. And then by doing so, we are conceiving such a system where all the nanosensors are traveling for all the human vessels. Because the human vessel have closed circuits through the arteries and then to the capillaries and then to the veins. And all these closed circuits are always closed here on the heart. Then we can conceive such a system, that is to use the vessels as the network to communicate what is happening, for instance, in this example, in this particular side of the human body, just to send, to go through here, then to sense these quantum sensing molecules, and then to report to a fusion center that we conceive located here on the human heart, on the heart, and we conceive such a gateway located on the skin, external to the human body, where the nanosensor will communicate with. That is, will send what is reported here, what was sensed here, specifically here, but this can be happen in any part of the body. Then, assuming this system, what we want to analyze here or to provide is to conceive such a clinical report, just to provide an alert that something is happening, that is, we detected some disease, in this case, these quantum sensing molecules released by this bacteria, and we would like also to provide some reliability level for this clinical report. And to do so, based on these mechanisms for all the nanosensors traveling around the body, then we conceive a two-branch methodology. On one side, we want to compute to this reliability level by computing this detection probability for one nanosensor to detect such specific molecules. And then on the second branch, we are interested in computing the total of nanosensors that might be present there in this specific region at this specific time. Because of the detection capabilities will be dependent not only on the capabilities of one single nanosensor, but for all the nanosensors that being there, then we need the two just to provide this reliability level. Just going through the different branches of this methodology, assuming just discussing this left branch on this side, then from this branch, we are computing the detection probability for one single nanobot in one specific tissue there. And to do so, we follow these 3 steps. One of them is just to simulate using console. This is something we did on the paper. We simulate the concentration level of quantum sensing molecules. Here on the top is the bacteria on the skin. And then these quantum sensing molecules are released in this way with this concentration level according to this graph here. And then the nanosensor will be located on the very bottom of this figure, just detecting this concentration level here. And then we provide such closed form expression using the binomial distribution just to compute what is the detection capabilities of in this specific tissue for all the nanobots that will be traveling there. And then we follow this formula. This is something we describe in detail on the paper, following a binomial distribution just to analyze all possible combination of the total of nanobots that might be there. And this will be dependent on 2 probabilities. One probability concerning the detection probability of one single nanobot here, but also the probability to find a given total of nanosensors there. Then both in conjunction, both together, and using this binomial distribution, then we provide this detection capability that we provide in somehow this reliability level for the clinical report. For one specific nanosensor, we model this probability as a ratio of the volume of the tissue and the volume of the specific region we are detecting. This is how we model this. And then using this equation here and using this simulator, then we provide this probability for one single nanobot to give there, to detect the disease. But we need the second one still for this Formula 1 that is concerning the total of nanobot to be specifically there at that time instant. To do so, then we go to the second branch of this methodology to compute this probability to find a total of nanosensor there. That is the second term of expression in 1. And then we follow on the second branch a different simulator. That is, we use the block YRS just to simulate the flow of nanobot through the different vessel segments, considering the arteries, considering the veins, and also considering the different capillaries. For instance, the right heart, the liver, the spleen, the intestine, for the upper arms, for the legs, for the center body, also for the head. And then based on this, we use a machine learning method to be implemented here on the gateway located at the heart, just to collect or just to classify the total of nanosensors that might be present in any specific tissue here. We do so by using a machine learning method to distinguish between the different traveling times for the nanosensor going through the different circuits. For instance, if one nanosensor departing from the right heart goes through this circuit to the thorax, to the center thorax, then the traveling time will be different if a second nanosensor traveled to the legs. Yeah? Then when we can distinguish between these two nanosensors, given the traveling time that they may report to the gateway. And this is what we use this unsupervised machine learning method just to learn what are the different sets of traveling time reported by all the nanosensors to the gateway here in this position. And based on this, then we can compute the distribution of nanosensor in probabilistic sense, the stationary distribution of them through the different tissues in the complete human body. Then we use this Cummings method just to introduce a Markov chain approach of the same method. This is something we discussed on the paper. And then this machine learning method will provide the transition probabilities for this Markov chain. And then based on the Markov chain is where we compute a stationary distribution of nanobots in the system with some probability. And from this stationary distribution, then we get this probability, a stationary probability to find nanobots in a given vessel segment or in a given tissue. And then we evaluate the second term in one just to provide this reliability level for this formula here. Then moving forward, just to conceive, just to explain how do we implement this machine learning model, we use the Cummings method. And then we follow these three different steps to cluster and then to provide this transition probability to the Markov chain. From the plot wire on the first step, we obtain a group of samples based on the total of iterations and the total of nanosensors. Then we get different timestamps depending on the circuit this nanosensor was traveling on. And then we're using the Cummings method just to cluster automatically and to identify also the total of cluster of the system automatically. And then based on this cluster concerning the traveling time for each different nanosensor, then we can compute the transition probability for the Markov chain model. And then based on these transition probabilities, we can compute later the stationary probabilities just to find a distribution of nanosensor inside the human body. Okay, then this is what we get from BlockWireS system. This is the distribution of timestamps that we get from the different human parts on the body. For instance, on the head, the traveling time is in between 40 seconds and 48. And then on the arms, we get the shoulders, the upper arms, the elbow, the hands. And then on the center body is where the problem becomes complex. That is, this is where the liver, traveling through the liver, the kidneys, the spleen, and the intestines, at least using the BlockWire simulator framework, provide this mixed timestamps. That is, it's not that easy to distinguish nanosensor coming from this region. And then from the legs, we have these three different groups. This is what we can use, the Cummings method, just to distinguish each different sets and then to properly classify each different nanosensor where it was coming from. And then we can compute the probability for the total of nanosensor being there. Using the Cummings method with this data, then we get this result as a silhouette diagram. That is, considering the different clusters that we may have, for instance, on the arm, we can cluster in each different segments, let's say the tissue on the shoulders, on the elbows, the upper arms, on the head, and the hands, sorry, then we get results close to 1, which is really positive. That is, the closer to 1 the result is, the better the classification system works. And also for the legs, we are really close to 1. But on the center body, it's difficult. And this is because of this, let's say, mixing of traveling time that we get using the BlockWireS. That is, the traveling time there are really close to each other. Specifically for the kidneys, for instance, and for the spleen, probably also for the pelvis. Okay, then we use also a second machine learning model also to provide an alert. That is, because this Cummings method, the unsupervised one, will demand a lot of time because he needs a large set of samples to do so. Then we cannot use this to provide an alert on the system that when a nanosensor provided that it detected some quorum sensing molecules there from a given bacteria, then we would like to give an alert as soon as possible. And then this is why we use a second supervised machine learning model that is specifically, we use a decision tree because also for simplicity, just to provide instantaneously an alert whenever we get a detection disease from the given nanosensor. And this second machine learning model will be trained by the first one. That is, all the labels and the samples will be already classified by the first one, and then these commands will be used to train this decision tree model. And with this second one, then we may provide the alert for the clinical report as soon as possible, almost instantaneously. Then for this second machine learning model, from the first step, we get all the samples, and then we use the Cummings method just to distinguish the different circuits. And then we take one of the labeled sample from the Cummings method just to train the decision tree. And then the decision tree may then instantaneously provide an output saying that this nanosensor is coming from one specific tissue based on this training. That is let's say that the second machine learning model will operate after this box, this red box, will operate with these samples here. This is the result that we get when we mix both machine learning models concerning let's say the capability to detect that the nanosensor is properly coming from this tissue. We have on this graph the several tissue from the head, from the upper side of the body, from the center body, and then from the legs. Because we do not have too many issues with the head and the upper body and the legs, then the positive predicted solution mixing the two machine learning models is one. That is, we easily can detect a nanosensor where it's coming from. This is not happening on the center body, and this is because all the samples are really mixed on the center body here. This is a future work that we would like to have, but at least we can distinguish that something is happening there. Yeah, that is in comparison to the legs and then to the upper arms. Going to the results for the last slide, using these two machine learning models, we can get also this graph. This is after computing the stationary transition probability from the Markov change, based on the transition probabilities provided by the Cummings method, then we can get, in a probabilistic sense, a distribution of nanosensors inside the different vessel segments. This is happening for the arteries. That is, the highest probability to find a nanobot there will be on the arcus aorta. This is an aorta that is an artery that is flowing through, going out from the heart, and this is expected to have the highest probability there. But then on the tissues, this is the distribution of probabilities that we have. Highest concentration is given on the heart, the lungs, and the left heart. This is also expected because all the circuits are closer on the hearts and the lungs, and then we have a high probability to find nanobots there. And then on the veins, the highest probability is found on the thoracic vena cava. That is, this is where all the veins are mostly collected, and then it is highly probable to find one nanobot here. And also, this distribution is really close to a previous work that we have presented to a previous conference with a different technique. We get more or less the same distribution. Yeah? This is something that we get after mixing the machine learning model with the Markov chain approach. And as a second result, we get a curve for the probability of successful detection based on the total of nanosensors that we have on the system on two different tissues, just to illustrate, on the shoulders and also on the upper arms. And then we get that on the shoulder, it is much more, we can detect much more easily than on the upper arms. And this is mainly based because on the shoulders, we get much more higher probability than on the upper arms to find a nanosensor there. Yeah. Also, we depict this curve versus a threshold level. That is, this threshold level is means that we say that something is happening there, that a quorum sensing molecule was detected if only one sensor detected, or 2, or 5. This is the meaning of this sensor here. And this is why this probability are reduced a little bit, because we are demanding to give an alert not because only 1, but because 2, or because 5. This is why we get this distribution here. Then this is a second group of sets for the curve for the reliability level that we might provide for this system. Just to conclude the talk, we provide a methodology to use this inherent body and working capabilities specifically on the human vessels. That is, we are already connected through the blood flow to early detect infections through the vessels. As a second conclusion, we introduced this machine learning just to support a wide applicability, because the machine learning might be really adaptable to the varying physiological parameters. That is, these solutions, because we are using this machine learning method or approach, this solution is not only applied to one specific body physiological parameters, but might be adaptable to a wide range of physiological parameters. This is the main motivation to use this machine learning model. And as future work, we have plans to apply this solution to study the performance of this methodology, but when considering different activities. That is, not only different physiological parameters, but also different activities concerning walking, running, or sleeping. Then the blood flow will be different on each different section. Then the distribution of nanosensor will be different. And then we want to analyze what might be the detection capabilities in this case. We thank for all your attention. We are open to questions and also to further collaborate. You can get in contact with us using this email. Please, thanks for your time and your attention.
Thank you very much, Jorge. Please thank the speaker virtually or on site.
Thank you.
Okay, so now it's time for questions. So I think there's one question live.
Hello, Jorge. Thank you very much for the very interesting talk and very detailed results. My question is a bit related to the keynote of Professor Lemme. So you presented really nice in-depth results using a simulator, using models. I was wondering if you have any ideas or future plans to actually validate these results with some kind of real experiments, or how do you envision this to be working with real nano devices? Have you thought about this?
Yes, this is a really hard question. We always have this in mind. For the moment, what we can do is what people used to do is to try on animals. On pigs, for instance, they used to try there. But also there are some artificial models that try to model the human vessels and the organs in some specific, something like circuits. This is currently a technology available, but really expensive. This is a potential direction that we might take just to simulate again, but in an environment that is pretty close to the human body, because this is already built with material that emulate really close the flow and the pressure in a scale to the human body. And this might be a direction we might take to do so. Thanks for the question.
As a follow-up to that question, so Blood Voyager, which your work is based, so that's a simulator, but is it based on real measurements of the blood flow, or it's like the result of some fluid kind of simulations? How does it work?
Yes, for the Blood Voyagers, we are using the reported solution from this paper, from Regin's paper. They implemented this in C++ code, connecting the head and all the tissues with segments, and they simulate, they may provide the location of particles traveling through the different vessel segments, also considering 5 different lines to travel with 5 different speeds through the arteries, through the veins, and also through the tissues. That is because on the vessels, we are traveling faster through the center of the vessel than to the, let's say, much more in the wall. Then this simulator also provides this detail. That is, they provide 5 different lines, streams, to travel through the different segments. Specifically, the parameters here are from a standard person, but this is something we can modify. That is, this is open to, this code is open to download and to interact with, and also to reprogram again. This is available to have it. It's open source. And then we can introduce any other physiological parameters and then to model any different variable. For the moment, this is for a standard person, following the curve of pressure and flow from a standard person in this case.
Standard person, I guess, and like not doing any activity. That's why your future work is also like considering different activities, right? Because the blood pressure would raise and reduce and so on. That would change the result. That's very interesting. So there's another question from the audience in Slack. Remember that you can go to Slack and make your questions for the rest of the day. So the question is from Philip Lemich. Could you please define in more details what the nanosensor in this context means? What would be the required functionalities for such a device?
Yes.
Particularly, if I might add my own question. So which is the precision in the timestamps that you need to actually differentiate between different parts of the body and so on?
Yeah. For the nanosensors, we assume that he has the capability to detect these quantum sensing molecules here. And then what we require for the nanosensor as a technology is to have this sensor incorporated, then to travel in a passive way through, he will be propelled by the blood flow through the human body. And then he doesn't have to, this nanosensor doesn't have to have any motor installed inside, because he will be propelled by the blood flow. And the second assumption that we have is that the nanosensor has such a technology that might interact with an external device on the body. That might be implemented with wireless technology, but also with ultrasound means, that is with ultrasound wave. This is something that is typically conducted on the state of the art to interact from inside the body to outside the body. For the second regard concerning what is the, let's say, the granularity level to provide how the total of nanosensor that might be specifically here, this is mostly based on the block wire simulator that we have. Because from the block wire, we can detect with this given granularity level, with this total of tissues, this total of vessel segments on the arteries and also on the veins, then similar happens on the Markov change. That is, the Markov change may provide the stationary distribution of nanosensor for the same total vessel segments like the block wire is. If we are able to introduce much more vessel segments, this is a direction we are also taking, then we can increase the total of stage here. Otherwise, we do not have enough data to model this Markov change approach. Thanks for the question, Philip.
Okay, thanks so much. So let's thank the speaker again. So we're gonna go for the next talk, which is given by Hadil Elayan. So please just start sharing your screen whenever you can. The talk is gonna be called Enabling Protein Interactions Using Terahertz Signals for Intra-Body Communication. And Hadil Elayan is currently a PhD candidate at the Electrical and Computer Engineering Department at the University of Toronto, Canada. She completed the bachelor's in 2015, followed by a master's in 2017 in ECE, in the ECE department of Khalifa University of the United Arab Emirates. She then worked as a research associate in the university's Healthcare Engineering Innovation Center until August 2018. She received several awards for her research and academic excellence including the 2019 and 2021 Ontario Graduate Scholarships, as well as the 2021 Photonics Expansion Grant. Her research interests include nanonetworks, terahertz intra-body communication, as well as molecular communication. So whenever you can, Hadil, the stage is yours. Thank you.
Hello everyone. Can you hear me clearly?
Yes.
Okay, that's perfect. Hello again, and welcome to this presentation. So today I will present basically our paper titled Enabling Protein Interactions Using Terahertz Signals for Intrabody Communication. The authors of this presentation are myself, Hadil Ilayan, a PhD candidate at the University of Toronto, Professors Andrew Eckford and Raviraj Advi. So the table of contents of this presentation is as follows. First, we're going through an introduction, then I'm going to introduce the system model, and mainly I'll focus on how to bridge the protein mechanical system to the probability of protein folding. Later, we'll go through the results, and finally, I'm going to conclude. So our work basically spans the room at the bottom, as described by the famous physicist Richard Feynman. Basically, the overlap between nanotechnology, bioengineering, sensing, and actuation, all for one purpose, facilitating the development of in vivo networks that would result basically in faster and more accurate diagnosis and treatment in comparison to in vitro devices. For this vision, basically to turn into reality, researchers took one further fundamental step, which is investigating paradigms in order to initiate reliable communication between nanomachines, since as we know, the traditional communication technologies are not suitable for nanonetworks due to both the size and power requirements. And for that, the two solutions that are available in the literature are molecular communication and terahertz nanocommunication. And in today's presentation, I'll be focusing on terahertz nanocommunication. So why terahertz? Well, nanoelectronics and nanophotonics, they point basically to the terahertz band in the range between 0.1 to 10 terahertz as the frequency range for communication among nanobiosensors. And mainly the suitability of the terahertz band for intrabody application arise due to two reasons. First of all, it is an non-ionization band, and this gives it the biocompatibility feature. And second, and more interestingly, the energy scale of terahertz radiation is within the range of interactions between molecules. Hence, it could be used basically to provoke molecules. So this is like the first part that I had in my title, so terahertz, but I also had proteins. And the second question that comes into mind is why protein research? Why are we so much interested in protein research? Well, proteins grease the wheels of nearly all the functions carried out in our cells. Understanding proteins allows us to understand gene expression. It allows us to understand structural biology, since the proteins and drugs are usually compared to the lock and key. Understanding proteins also allows us to more deeply understand how misfolded protein aggregates accumulate in the human body, and as such, how neurodegenerative diseases, what are the nature of them, and how basically Alzheimer's, Parkinson's, and many other diseases basically are formed. And most importantly, by understanding proteins, we would further understand neurons, and hence this gives us, how can I say it? It gives us a feeling of, or an understanding of how brain research should be basically properly done, and what are the signal transduction pathways that are found in the brain, basically. So I would say that understanding the protein molecule is basically a key into understanding further intrabody pathways that are found in the human body. So we had terahertz, we talked a little bit about proteins, but the question that I believe all of you have in mind is why proteins and terahertz together? Well, the reason is that the vibrational modes of proteins are found in the terahertz frequency range. So our system, or we envision our system to be composed of a nano antenna transmitter and protein receiver, where we can provoke basically the protein using the nano antenna. These modes, the vibrational modes that I'm talking about, are important because they are the ones that control the protein conformal changes, the ligand binding, and oxidation state. So imagine it this way. Triggering the protein vibrational modes is going to cause mechanical signaling in the protein, and hence we are going to have a structural change and an activation of biochemical events. And this occurs basically by provoking a resonant interaction. So by setting the nano antenna frequency to the frequency of the vibrational modes of the protein, resonance is going to occur, and here I'm going to have an upsurge in amplitude, which should be translated into channeling of energy that is going to be modulated through the human body. So this is in glance how the system basically is composed, I would say. Now, for work on the literature on terahertz protein interactions, the most relevant work that we can see is the work of Professor Andrea Markels. Professor Andrea, she works on terahertz optical techniques for protein dynamics characterization, where they do some experimentation in the terahertz frequency range, basically on proteins. Our work basically focuses on protein terahertz interaction from a sensing and from a communication perspective. So what we are hoping basically to do is that to develop a stimuli responsive paradigm that is going to deploy terahertz waves in order to allow further interaction with molecules and the control of transduction pathways. And I believe that this could be basically the link between the terahertz nanocommunication approach and the molecular communication approach. You have a terahertz source, you provoke proteins are going to further provoke intrabody interactions at the molecular level. So just also to give you a feeling of these vibrational modes that I'm talking about. So in the literature, example of protein resonant values at terahertz frequencies, for example, we have the chemical reactions in myoglobin, they occur at 1.5 terahertz, conformal change of lysozyme at 2.8 terahertz, detection of DNA nucleotides occurs in the range between 1.31 to 1.326 terahertz. So it is these frequencies that basically we are interested in targeting based on the protein type. Now, how does that work from an electromagnetic perspective? So what is going on? Like how is the interaction going? Well, the nano antenna electromagnetic field basically results in the polarization of the protein molecules. And since the proteins are polar, they already have a net permanent dipole, which gets rotated in the direction of the electric field. Now, when the electric field gets reversed, the alignment of the dipole is going to change. And as the frequency increases, the applied input and system response are no longer in phase. And basically what happens, the proteins become characterized by their complex permittivity. So here in equation number 1, this is the real part of the protein permittivity. And usually polar molecules in the terahertz band, those permittivities are calculated, or they are found numerically using Debye processes. So people who work in the field, they are usually used to seeing the permittivity, but they are usually mainly used to seeing the relaxational response of the molecule itself. However, what distinguishes protein from other molecules is that not only does it have, this relaxational response part, which we are used to seeing, but the key is that it has a vibrational response. And this is what made it of interest and made it interesting. It has this omega 0 factor here, which is basically the natural frequency of the protein. And it is this omega 0 basically which we are intended to target. We are intended to set the nano antenna to the frequency, to the natural frequency of the protein in order to see how our resonance reaction can basically take place. Again, this is also the imaginary part of the protein permittivity. Also, it has a relaxational response and a vibrational response. The relaxational response basically arises from the amino acid side chains, while the vibrational response, it arises from the correlated motion of the protein molecule. Basically here, when I'm talking about correlated motion, it's that many parts of the system basically oscillate at the same time. And this collective motion is a crucial part in functional response. Think about it this way, as a cooperative effect that is attributed to the interaction between the subunits basically of the protein. So the two take-off messages from this slide basically is that first, protein structures are not transparent under terahertz electromagnetic radiation, and their contribution to collective motion cannot be described as solely arising from relaxational responses. And basically, this is what lightens up the capability of invoking resonant interactions. So this brings me to basically the research question, to what we are basically discussing. Well, we want to see how we can bridge the mechanical system of proteins modeled as harmonic oscillators with the probability of protein conformal change. We want to see if we trigger the proteins using terahertz EM waves, can the probability of proteins being in a folded state change? In order to do so, we are going to follow this procedure. First of all, we are going to use the Langevin equation in order to capture the protein dynamics. Then we are going to find the total energy of the protein stimulated by an external force. And later we are going to incorporate the steady state energy of the driven protein into the Boltzmann distribution. So here how it goes. First of all, we have the Langevin stochastic equation, a second order differential equation here. M is the mass of the protein, beta is the damping coefficient, K is the protein stiffness, X of T is the coordinate of the protein, and we have our forces. We have the external force, which is due to the nano antenna, as well as we have the stochastic force, which results from the Brownian motion of the particles surrounding the protein. And the solution to this equation basically can also be decomposed into two parts, which is the part that is due to the external force, as well as the part due to the stochastic force. So our aim basically is to solve this equation under those two forces. So in order to do so, mathematically, we are going to use a Green's function. Green's function basically is the solution to the differential equation with a forcing term that is given by a point source, which is basically the delta. And the good thing about it is that the solution to the same equation can be found for any arbitrary term, basically by integrating the Green's function against the force. So basically what we are interested in finding is what is the form of a Green function, so that we can use it with each of the external force and with the stochastic force. So here in equation 6, we have the frequency domain solution of the Green's function, and then we take the inverse Fourier transform in order to find the time domain solution, which is basically we are interested in. And then we have equation number 8, because this time domain form of Green's function is what is going to be used with the external force and with the stochastic force. Now, in order for equation 8 to be definite, basically this condition has to work. Basically, we have omega 0, which is the resonant frequency of the protein, has to be greater than gamma. Gamma here is damping over 2. And this is interesting because basically this satisfies the protein vibrational motion, where protein modes in the terahertz are underdamped. And this is proven experimentally that these modes which occur in the terahertz range are underdamped. And why I'm saying that this is interesting, because this means that the lifetime of the excitation is in the order of picosecond, and as such, vibrations propagate underdamped by the thermal fluctuations in the medium. So the thermal fluctuations in the medium cannot basically overtake this vibration that I'm talking about. And this is the key idea, is that these resonances are going to live in the system. So the solution corresponding to the nano antenna force is expressed using the time domain Green's function as. So this is the solution, which is for our external force. We have this is Green's function, this is the external force, and we get a final form for that. The same thing we do for the stochastic force. So the idea, as I said, is just to solve equation 3 that we had previously in the slides. Why is that? Because from the solution, we are going to compute the total steady state energy. So basically, this is the link. So think about it this way: the exposure of protein molecules to the nano antenna terahertz radiation is going to cause an energy built up within their structure. This localized energy is too low to cause any ionizing damage, but it's going basically to lead to significant effects at the cellular, organelle, and macromolecular levels. We find the total energy of the protein stimulated by an external force by computing both its kinetic and potential energy contributions. So basically, we are going from this X of T that we found under both the external and the stochastic force, we are going to find the steady state displacement, and we are going to find the steady state velocity. And this is why initially we had to solve the Langevin equation, which we believe capture to a great extent the what is going on, or the motion of the protein. So after doing several derivations which are found in the paper, we reach basically the final form of the equation here given in equation number 16. And this is here the total steady state energy. The total steady state energy, we can see it has two contributions. It has a terahertz force contribution. So this aspect resulted from the terahertz force, and we have the noise effect. And here this gives us an insight. First of all, it tells us that for resonances to have an important effect on biological system, the system must absorb energy in excess to the thermal noise. Hence, the system cannot be affected by an applied field if its effect is mainly less than the corresponding random field. Also, interestingly, we see that the contribution of the thermal noise satisfies the equipartition theorem, i.e. every degree of motion, it has contributed equally to the noise component in the system. Finally, the final part would be to link this energy function to the probability of conformal changes. And for this, we are going to use Boltzmann distribution. So in the literature, the rate of protein folding is given by equation number 17. Here, R0 is just a scale factor, and EF here denotes the free energy, which is stored in the protein associated with it being in a folded state. We are going to amend equation number 17, and we are going to incorporate the total steady state energy that have been computed. And we are computing, by the way, the energy in the steady state because we are interested in the stationary probabilities at the end of the day. Then we have the folding. For the unfolding, it's going to be a relaxation process because the protein cannot stay in the folded state. It is going to return back into the unfolded state, and hence we can see equation 19, it's independent of the imposed signal. We find the rate of change of the probability, which is given by equation number 20. And the idea is to find the stationary solution, which is the key here is equation number 21. We already know the rate of being in a folded state, which we have incorporated the total steady state energy into it. We have the rate of unfolding as well, adding, like replacing back these components. We are going to have equation number 22. So equation number 22 is the probability of the protein being in a folded state after being exposed to the terahertz frequency range. So how do the results look like, or where do we want to reach with those results? Let's have a look at basically the results. In order to do so, we have considered two protein molecules that are in the vicinity of one another to mimic an interbody environment. Those proteins which we considered are rhodopsin and bacteriorhodopsin, we chose them because they are fully characterized in the literature. We can see that the resonance frequency of rhodopsin, it occurs at 1.36 terahertz, and for that of bacteriorhodopsin, it occurs at 1.13 terahertz. We have the stiffness and mass for each one of them. So here we have in figure 1, we have the probability of the protein being in a folded state versus the nano antenna force. For both rhodopsin and bacteriorhodopsin, in this figure, the resonant frequency is set to that of rhodopsin, i.e. so the nano antenna is tuned to the frequency of rhodopsin, which is the 1.36 terahertz. And this is important to note. I'll tell you why in a while. For the other parameters, we have the damping value set to 0.3. We have the free energy value taken from the literature to be 6 kb. And we can see here, okay, so I'm having force. This is what I'm saying is the nano antenna force. We can see that the rhodopsin basically reaches a folded state at around approximately 70, I would say, piconewton. And we can see for bacteriorhodopsin to reach a folded state, it takes it more. It takes it around 200 piconewton, basically. And what does that tell us? It tells us because I'm setting the system to the resonant frequency of rhodopsin, it's going to acquire a folded state much faster, or with less force in comparison to the bacteriorhodopsin protein. And this makes sense. This is the idea of basically setting the system to resonance, because you want to you want to induce a conformal change in the specific protein and not in the all proteins. And this gives us also an insight that the force range here shouldn't be chosen arbitrary, because at the end of the day, you don't want to provoke all the proteins in the system into a folding behavior. You need to be very selective in order to impose controllability on the system. Think about the reverse case, that we are setting the resonant frequency to that of bacteriorhodopsin, and here we can see that the bacteriorhodopsin, it needs a lower force when it is at its resonant frequency to reach a folded basically state in comparison to that of rhodopsin. So I'm going to finish. I just have one or two slides left. So here, just the other here what we have is that we have the probability of the protein being in a folded state versus frequency for that of rhodopsin and bacteriorhodopsin. So we can see that at the resonant frequency of bacteriorhodopsin, the probability of being in a folded state is higher in comparison to that of rhodopsin. This is basically due to the fact that, as we can see here, that the bacteriorhodopsin has a smaller mass and it has a lower stiffness, and hence it's easier to put into a folding behavior. But still, at the resonant frequency of each one of them, we can see that it acquires a folded behavior. If we further increase the damping in the system, what happens is that the probability of being in a folded state for both frequencies are going to reduce. So the takeoff here is that if we set the frequency to resonant for either rhodopsin or bacteriorhodopsin, the probability of the protein being in a folded state is going to basically increase. So this brings me basically to the end here in our research. What we're trying to do is that we're trying to bring closer together the fields of molecular and electromagnetic communication. And basically, we're focusing on the link between the nano antenna and the protein, as well as on the induced protein responses. And we hope through this research to advance the EM-based control of the proteins, which we believe is going to have a great impact on signal transduction. There is a lot of research gaps. For example, one of them would be developing a complete system model, understanding the timescales of the nano interactions, understanding the different protein states, and for sure model validation through experimental work. So as exciting as the work is, as challenging it is. And again, we're also happy and to collaborate with anyone who could be interested in any part of this project. So feel free to contact me at the email. Sorry for the lengthy presentation, and I'll be happy to receive any of your questions.
Thanks so much, Hadil, for this very comprehensive presentation. So let's thank the speaker. Okay, so any question from the audience live or from home, Slack? None? Otherwise, I can make a question. So that's very interesting. It seems like you're kind of removing the need for an actuator in the nanosensor, right? Because you're actually using terahertz waves to make these actuations somehow. So that's a very interesting thing. Can you give us an example of how protein folding can cause or inhibit one response in proteins that might be, I don't know, relevant for the biomedical community?
Actually, there are like several examples. Let me talk about, for example, quickly the protein rhodopsin. For example, protein rhodopsin, it is a protein which is basically related to vision. And the idea here is that several mutations can arise even when proteins fold. For example, they can be misfolded, and then when, for example, the protein gets into a misfolded state, well, here it cannot perform its functionality properly, and then these misfolded proteins are going to aggregate, and further they are going to cause diseases. So the idea here, if we know, for example, here we know what is the vibrational frequency of rhodopsin, and if we can get this knowledge that this protein is basically causing the issue, well, we will be trying to trigger that specific protein in order, for example, to bring back the system into its normal behavior. I know that sounds a bit of its implementation wouldn't be for sure that easy, but the idea, as you said, as you mentioned, is the fact that as long as I know these vibrational frequency of those proteins, and I know what kind of functionality, what kind of mode basically they control, by triggering these modes specifically, this can provoke the protein back into its original folding behavior, and as such, it's going to carry back its functionality.
Okay, thank you very much. I don't think we have more time for more questions, but just let me comment that, with this AlphaFold by DeepMind that is going to release all the folding structures of the proteins at some point, it might be interesting to see how that can be used. And also, it poses a question on whether now we can think of terahertz communications between nanosensors, because it seems that they're going to be interfering with. So these communications are going to be interfering with the protein. So maybe that's something interesting to study. So thanks so much, Hadil. Thanks for the presentation. So let's thank the speaker again. Okay, so now very quickly, we're going to move on to the third presentation of the session by Daniel Martin. So Daniel, wherever you can, start sharing your screen. In the meantime.
Can you hear me clearly?
Yeah, we can hear you. So you can start sharing your screen whenever you're ready.
Okay, just a sec.
In the meantime, let me just give you a few words about Daniel. Daniel Martins is a postdoctoral researcher and the technical lead of the biomedical nano and molecular telecommunications team at the Walton Institute in Ireland. His research concentrates on the modeling and analysis of conventional and nanoscale communication systems. He received his PhD from the Waterford Institute of Technology, Ireland in 2019. So Daniel, the floor is yours.
Okay, can you see the slides?
Yes, perfectly, thank you.
Okay, good morning, everyone. And thanks, Sergio, for your nice introduction. I'm Daniel Martins. I'm a postdoctoral researcher at Walton Institute. And this work is a collaboration of three different institutions, two from the Waterford Institute of Technology, which is the Walton Institute, and the Pharmaceutical Molecular Biotechnology Research Center, the PMBRC, with the University of Nebraska-Lincoln. So the authors of these papers are myself, Jennifer Drohan, Sarah Foley, and Lee Coffey, and Sasitara Subramania. Both myself and Sasitara, we were working on the theoretical side of this work, while Jennifer, Sarah, and Lee work on the experimental side and developed the experiments that and the result that the experimental result that I will show you in a few moments. So, what's the whole idea of this work? On this work, and sorry to come back, it's I forgot to mention the title of the paper. It's a modulated molecular channel coding scheme for multibacterial transmitters. So the whole idea of this work is that we are exploring and exploiting the ability of bacteria to send and use molecules. Okay, and typically bacteria use molecules to perform coron sensing, which is a form to get to know exactly the amount of bacteria that are living close to each other. So they use that to measure how much they are in that particular location and make collective actions based on that. So, for example, they can start to colonize a particular surface. They can start to produce some virulence factors, which can drive us sick, for example. They could form biofilms and so on. So all of them depends on the amount of bacteria that lives in the same area, the same location. So one interesting thing about the coron sensing and this ability of bacteria to use molecules is that the bacteria can modulate this production based on external stimuli. So if you apply light, if you apply electrical current, or even if you apply any external chemical input into the bacterial population, you can drive the production of these molecules to be more or less depending of the level of that particular input. Okay, so there is a lot of different applications that already have been built looking for electrostimulation, photostimulation, and even chemical stimulation. So here, with what we are doing, it's we are building a molecular communication systems based on this coron sensing, and using a chemical stimulation. Okay, so we are looking to how stimulate chemically the two bacterial populations to produce signals as shown here on this slide. So we are using different chemicals to induce these bacterial populations to produce more or less signals as we want. And then after that, we have a certain combination of molecular signals. So it's not going next. Yeah. So what happened is we combine these different molecular signals to create what we are showing here in this figure as an encoded signal. Okay, and by doing that, what we want at the end is to find a nice combination of different molecular signals emitted by different bacterial populations to create different channel codes. Yeah, so coding has been applied to typical communication systems for quite some time, and they are used for different purposes. We have source coding, we have channel coding. In this specific, this paper covers the channel coding, but the channel coding is applied to protect the signal against any effects of the channel. So if you have multipath, if you have sort of fading effect, so you apply channel coding, you increase the number of bits in simple terms, You just increase the number of bits or create a different way to represent that number of bits with more bits to make sure that the signal is protected through anything that can happen in that particular environment. And there is loads of different techniques to do that. There is convolutional codes, there is plenty of different codes. But in molecular communications, there are not so many. And mostly are applied looking from the same perspective of communication systems, like trying to create an algorithm to create that particular code or to apply convolutional coding and produce and protect the signal to increase the performance of that particular molecular communication system. In our case, it's a bit different, okay? So we are looking first from the perspective of the bacterial population, or how the bacterial population produces the signal and how we could exploit that. So first, we look for the ways that we can modulate the signal, okay? So in molecular communications, we have CSK and molecular shift keying, which are two different modulation techniques that are applied on the variation of the amount of molecules that we are able to output from a particular nano device. Okay, and here what we are doing is we are mixing these two. We are mixing the modulation of signal with the channel coding to create our molecular channel code scheme. Okay, so here what you can see in this figure, we have the molecular signal that's being output from a bacterial population. Each will be encoded to create in our case, a concentration shift keying modulation, okay? And then we'll pass through a channel encoder, which will change the signal a bit, and the signal will be propagated up to a receiver, which will decode the whole system, okay, in the back. The interesting part of this approach is that we could use any kind of device to detect the signal, because we are not changing the nature of the signal. We are just adding more molecules to the process. The thing that we need to be careful at the end of the process of the receiver is how to separate these additional molecules, okay? And I would like to emphasize that our channel encoder is another bacterial population, okay? So we are using two bacterial populations, one to propagate the signal and another one to encode. So how this can happen? This is based on the ability of bacteria, as I mentioned again, to emit, produce, process molecular signals. And this is based on the chain of chemical reactions, okay? So the bacteria has specific signaling pathways that are able to process these molecules. And we can exploit that by changing the plasmid, which is the specific DNA that bacteria have, that are instructions to what the bacteria can do, okay? And what we do in this particular paper is we simplify this approach, we simplify this analysis to model this signaling processing as a transfer function, and this transfer function will be dependent on the number of receptors that the bacteria will have and the type of molecular species that we are using, okay? And by doing that, we were able to use two different bacterial populations. One's called MCATE, and another one is wheat globe. MCATE producing red light, and wheat globe producing green light. So the channel coding scheme is quite simple, okay? Despite the whole mathematics here. What we really do is we use rate reaction equations to create the model for the modulation of the signals produced by MCATE and wheat globe, and encode that using CSK to create multiple concentration, to define multiple concentration thresholds, and define from what to where we were considering that's a 0 or a 1, or a 0, 0 or 0, 1, okay? And in our case, we are considering that we have 3 different thresholds for MCATE, while we have one single for wheat globe. And by collecting the results of this equation, and let me present this, the source encoding is represented by this set of equations here, while the rate reaction equations are represented by these equations on top. So we combine the results coming from this source encoding using this, this representation is not an equation, it's just a representation where we are selecting the lower and the upper points of the threshold of the range of possible values to define where we are in the code and define the code itself. Okay. So let's look for the results, which might be more clear exactly what I'm trying to say. So for this case, for this analysis, for the numerical, for theoretical analysis, we use two molecular input signals. So the bacteria will receive two signals, and one is control, where we vary the amplitude from 0 to 4 millimoles. And we just use single pulses with a really short duration to represent the timing that a person would, for example, input that signal manually in an experiment. Okay, so looking for this plot, we can see that we defined that 3 different thresholds. Okay, these 3 in the middle, one here, and another one here for MCATE, while we have a single for the witch glow, which is here. Okay, and by combining the values within the ranges, like here, here, and here, we define a set of codes that we are using to transmit the information. Okay. Another interesting thing here that we can see is that we are using the same, pretty much the same signal between the 2 bacterial populations, which is an interesting point, because that means that you can build this code with any configuration. It's just a matter of how you define the amount of molecules that you are able to output. Okay. And here we will have this sequence of codes that we are able to build 00, 001, and so on. We were able to create 8 3-bit codes by doing this analysis here. As I mentioned, the signals are quite similar for both MCATE and witch glow, which, despite is an interesting thing from the coding perspective, is bad for the signal reception, because it might be that we might not be able to discern exactly which is which is an issue that we are going to face in the future. And this is also results in intersecting code. So depending how you define the ranges and the thresholds, you might have some intersections, some overlapping. And that what can do is really in reality, and you will see that on the experimental results, is that you are not be able to have 8 codes, but 4, 5, 3, and that's a challenge that we need to work for the future, is to define really well the thresholds to avoid this issue. So just to give an interesting introduction of this process of how we engineer the plasmids and how we engineer the cells to produce these 2 signals. This is the transformation of a bacteria, which is a process in biology that defines how you insert external plasmid into a bacteria. The bacteria receives that plasmid, will live for a certain period, will use that to increase their own population, and then assume that plasmid as its own. Okay, so this is how it happens. So you mix them two, apply a heat, then the plasmid will be inserted into the bacteria. The bacteria will assume that plasmid, and then will colonize. You created a bigger population, and then you have the population ready to do any kind of experiments that you have that you want. In our case, is to produce light, produce results. MCATE was gifted by Michael Davidson, so the gene and the bacteria was already ready for us, so we didn't have any kind of action on that. But witch glow was a plasmid developed for an old project of us that we used to encode DNA. So we use that same we use the same plasmid that is able to encode information into DNA to simply produce signals to create this molecular code. Okay. To induce MCATE to produce the signal, as I mentioned, we are controlling one signal between the two. We use arabinose, and for witch glow we use IPTG. And the fluorescence, this that you can see represented in this figure, was measured for 5 hours. So these are the results that we're able to get. For MK, you can see that has there is a nice separation between the code 00201 and 10, but when you look to these two results here for 5 and 6 on 11, you can see that are quite close, and the same thing as 1 and 2 for 00. So there is some sort of overlap here that not allow us to have as many codes as we want. The same thing we have for the which glow, as we just use one single input, that's nice because you just need to make sure that we achieve that threshold and that's it. We don't have as much trouble to produce the code that we want. In this case, it's just one. And we combine them together afterwards to produce this final result here, where we have the sequences of these 4 codes 001, 011, 101, and 111. Okay. I need to mention that this was done after. We were not mixing the 2 bacteria populations during the experiment, because that can produce all the result that not intended. And to simplify that, what we did was we run one for the MK, one for the witch glow, and then mix the two productions to get this final result here. Okay. And then can be done also looking the perspective of applying these in interbody communications or in any other application using bacteria, engineered bacteria. So we can create small capsules where we have the bacteria inside there producing the signals that we want, and then just have another chamber, another capsule, just combining the 2 results and use that to your purposes, okay, to your particular application. In conclusion, what we are able to show here today to you is that we are proposing a novel molecular coding scheme, which is not really looking into how to protect the signal to improve the performance of the signal, but to protect the signal to ensure that we have the measurement that we want at the end of the process. So what we want to have is a way to combine multiple signals that we would find in nature. And even with that, we are able to retrieve the signal that we want, okay? And for doing that, we are using multiple bacterial populations and multiple signals. And we just use 2 bacterial populations here and 4 signals, but we can amplify that to increase that for any number. It's just, as we increase in the numbers, we are going to increase the complexity of this process, of this analysis, okay? And we truly believe that this work will facilitate the design of novel bacterial-based transmitters and other bacterial-based engineering devices that can be applied for interbody communications, for environmental monitoring, for animal monitoring as well, okay? Because we are just making sure that we are able to retrieve the signal that was detected, processed, or computed by the bacteria. And we're now making that using this approach of the coding. And I want to thank you all everyone that supported this work, both the Waterfall Institute of Technology, the TSSG, now Walton, PMBRC, and Chagas, because and my funding agencies. And that's pretty much it. If you have any questions, please feel free to contact me. If you want to collaborate, I'm open to any collaborations. And yeah.
Okay, great. Thank you, Daniel. Let's thank the speaker. So any question live from the audience or in Slack? Otherwise, I have one. So you mentioned that you can extend that to multiple species, not only 2 as you have in your example. Mm-hmm. So have you theorized a bit about the scalability? So how many of these species you can support? And the other question would be, does it provide any benefit beyond or compared to just having more levels in your CPSK? Meaning, instead of having QCSK, if you have 8 CSK or 16 CSK, so having more bacteria or colonies, does it provide a benefit compared to that?
Okay, so we can look from answer your first question about the number of bacterial populations. We can, let me go back here. For the equation, just to get a nice idea. So what happened is multiple bacterial populations, multiple signals means multiple equations to deal with, and probably need to be more careful in the definition of the thresholds and how to combine these signals, okay? This combination was made in a simple way, defining the upper and lower bounds, just because of we have only 2 signals applied on that on this purpose. But maybe it's not so scalable if you want to have as many. But the whole idea, the framework and the background of this idea is applicable for any number of bacterial populations. So the thing that made that's gonna happen for sure by adding more bacterial populations, more signals, is that we're going to increase the complexity of this model. We will need to add more equations. We need to add more controls for these systems to make sure that we have the signal that we want at the end of, and at the receiver. Okay, that's the point of adding more. From the application perspective, why we want to increase these numbers? Typically, in a natural environment, bacterial populations are surrounded by many bacterial populations. Okay, so that's not a usual thing to have one single population is pretty much lab experiments. So the idea that we want to apply these multiple bacteria, increase these numbers, is to get as close as possible to what could happen in nature, because if we add a new bacterial population, let's think in that sense. If we add a bacterial population to sense a particular disease in the body, biomarker, and you just engineer MCATE, just for sake of explanation here, just engineer MCATE. We are not engineering which glow any other bacterial population, but you have as other bacterial populations, and these other bacterial populations would act as the encoders of this system. What we need to do is to know how that could happen, what could be done with this system, what would the result be, to be able to detect the signal from MCATE and use that as a way to monitor really the disease. Because again, if you apply the bacterial population, the engineered bacterial population, inside of a body of a person, or animal, or even the environment, you are going to have many other signals there. We'll have loads of noise, and we can use that noise as a way to encode the information, as protecting the information itself, and collecting that as the end of the process, if we know how to do that. And that's the idea behind of this encoding, is that we can look that in the perspective of encoding, by increasing performance of a system. But we can also use that as a countermeasure to noise or any other effect that can happen in the environment, naturally can happen in the environment, just by knowing how that could be modeled, or how that could be.
Daniel, I need to stop you here because we need to move on to the next speaker. So thanks so much, Daniel, for the presentation and the very, very comprehensive explanations. Thanks so much. So let's thank the speaker again. Okay, so now we're going into another highlight of the program today. We have the honor to have Nick Van Helput, and sorry if I didn't pronounce that correctly, from IMEC, with the title High Density Neural Interfaces Using Active Silicon Probes. And so yes, Nick, whenever you're ready, just please start showing your screen.
Yep.
In the meantime, just a quick word on Nick. So Nick received the Master of Science degree in the electrical engineering in 2004 from the Catholic University in Leuven in Belgium. He received the PhD in the same institution, and his research focused on low power, ultra wideband analog front-end receivers for region applications. He joined IMEC in 2009. and he did lots of things since then. But he joined as an analog R&D design engineer, and he's currently scientific director of the Circuits and Systems for Health in IMEC. His research focuses on ultra-low power circuits for biomedical and life science applications. He has been involved in analog and mixed signal ASIC design for wearable and implantable healthcare applications, and that's going to be the topic of today. Nick is an IEEE and SSCS member, distinguished lecturer from 2017 to 2018, and served on the technical program committee of BLSI Circuit Symposium on ISCC, which are very, very prestigious. So Nick, the floor is yours.
Thank you. You can hear me fine, as well as see the screen?
Yes, we hear you fine, and we
Okay.
can see your screen. Thanks so much.
Okay, thank you. So thanks for the invitation, first of all. And in today's talk, I want to share with you some of the work we've done on developing silicon neural probes. So we started looking into this a few years ago to basically tackle the bigger problem about unraveling how our brain works, and particularly how certain neurological disorders work. So as you all know, the brain, it's an incredibly complex organ, and just like any other organs, it's susceptible to a lot of specific diseases. There's a lot of neurological disorders. And on the one hand, there's still a lot of unknowns about, first of all, how fundamentally our brain works, as well as some of the pathologies of these disorders. And secondly, there's an increased need for, well, there's a continued need for more innovative therapeutic as well as diagnostic solutions. And that's a little bit where this work is framed. So we want to develop digital neural interfaces. We want to develop technology that's able to record activity from our brain. So, and one approach of doing that is to build custom chip solutions that can directly interface with the nervous system. On the one hand, its main purpose, as already mentioned, is to develop new tools to help fundamental neuroscientists to understand how the brain works, how certain neurodegenerative diseases affect our abilities, as well as how brain's computing principles can be used to also build more AI-based computers. But it also is a segue into next generation medical devices like prosthetic devices, therapeutic devices for neurological disorders, and maybe longer term also for brain-machine interfaces. But I want to focus more on the first aspect because that's also our current immediate focus, developing tools that help fundamental neuroscientists understand how the brain works. And if you look at the human brain, it's actually a very complex and very dense network of neurons. Just in 1 cubic millimeter, you can find around 50,000 neurons and 500 million synapses. So it's an incredibly complex network. And even though individual neural cells and neural communication can be thought of as reasonably simple, the complexity stems from the enormousness of that network. And if you look at the tools that neuroscientists had available to understand at a fundamental level how this network works, well, it started a few decades ago with these large rack-based equipments that they could hook up to patch clamps and electrodes that essentially were able to record from a handful individual neuron cells. And then gradually the technology has been pushing towards a scale up, parallelizing, reading from more and more electrons and neurons, and making the equipment smaller and smaller. And that is, of course, an area where CMOS industry is really, really good at scaling things down very aggressively. And that's before I dive into the technological solution, I want to briefly mention what actually is neural recording? And conceptually, you can think of a large football stadium, for example, with a huge crowd. And obviously, every person in this image represents an individual neuron. And you're actually trying to understand what's going on in the football stadium by putting a microphone there, listening to all of the sounds, and trying to understand what happens. You can obviously put the microphone very high and you will collect not the individual chatter, you'll basically collect the general gist of what's going on. If a goal is made, definitely you'll know that from picking up, but you don't know the individual interactions. You can drop the microphone down right in front of one or multiple people, and you might be able to understand how they talk. But there's a lot of background noise as well, and that's essentially a good analogy of what the challenge is when we're doing neural recording, when we're building systems for neural recording. What happens so between two individual neural cells? So they communicate with each other through an electrochemical process, and I'm not going to explain the details there, but suffice to say that it's an electrochemical process involving neurotransmitters. And essentially, one neuron can signal to another neuron. And when that happens, there is a small electrical signal that's being generated, which we typically call an action potential. It usually has a shape which is similar to what's drawn here. So it looks like a spike. Often people refer to these signals as spikes, and they occur when a neuron fires. So these are etymologies often used. And essentially, when we're building neural recording circuits, we're building circuits that are picking up this small electrical signal, either from an individual neuron, in which case we're really recording individual action potentials, or if you put your electrode, you make your electrode larger than individual neural cells, you basically get an aggregate of the electrical activity of all of the neural tissue in the vicinity of your electrode, in which case we talk about local field potentials. Or if you really move further away, we talk about really aggregate activity, like in what you would record in an EEG or things like that. If we really go down to individual cellular level, you can either record what we call extracellular. If you bring the electrode, and here I've drawn an old patch clamp, but it could really be just an electrode itself. If you bring it close, but still outside the electrical cell, you're recording extracellular activity. You see these action potentials, and the typical amplitudes are tens to a few hundreds of microvolts. You can also go inside the cell, and then you'll record intracellular activity, which is much larger, but that's not often done a lot, because again, that's not a scalable solution when you really want to record from a large number of neurons. So in order to really help neuroscientists understand how complex processes in our brain work, you actually want to be able to record that individual neural activity over a fairly large region of the brain. Now, there are multiple technologies available that can record from the brain. And in this slide, I'm showing the difference between the spatial resolution of different techniques, which means how small of a signal can they resolve in space? So how close to an individual neural cell are you coming versus the temporal resolution? So that dictates how long it takes to do a signal recording, and as such, whether or not you can do measure dynamic behavior and dynamic processes. So what you see here is EEG, which is a non-invasive method. It involves putting electrodes on your skull, and recording the electrical activity, very similar to, for example, a heart rate recorder. Because you can put electrodes all over your skull, it can actually cover most of the brain. So the pie itself represents the coverage of the full brain. So this is a technique that's capable of measuring all of the brain activity, and actually a reasonably good temporal resolution, but a very poor spatial resolution, because of course you have fairly large electrodes far away from individual neural cells. It has very poor spatial resolution. There are advanced imaging techniques like MRI that offer really good spatial resolution, in some cases down to individual neural activity. These can also cover reasonably large parts of the brain, but they have a very poor temporal resolution. They're also very expensive, not convenient to do. And so there's definitely a need to develop technology that has good spatial resolution at good temporal resolution. And that's where silicon neural probes come into the picture. So they try to record electrical activity with a good temporal resolution and a good spatial resolution. But of course, they can't cover a significant part of the brain. And obviously the pie is not to scale here, because we're not even close to 1% of covering the whole brain. So there's really a need to develop more and more technology in this area here, going for high resolution probes that give neuroscientists tools to really understand complex function of the brain. And actually, there is something similar to Moore's law in neuroscience. What you see here is the amount of simultaneously recorded neurons versus publication years. And as already mentioned, when the whole field started a couple of decades ago, people were looking at 1, 2 to 10 types of neurons being recorded. And with technology scaling, we can roughly see a doubling of the amount of neurons we are able to record concurrently every 6.5 years. So that's it is an exponential law, but if we would follow this law, it would take us 200 years to reach full scale of a human brain. So we need to find a way to really break this trend, and that's where, to a certain extent, high-density neural recording comes into the picture. The idea here is that we actually build silicon chips that have these needle-like structures, and this is really part of the CMOS chip. I'll explain this later, where we can use the feature sizes of CMOS, which are in the same ballpark as individual biological cells, to build a whole array of hundreds to thousands of electrodes at the physical size of individual neuron cells, and have on the board all the necessary amplifiers, digital filters, and ADCs to record parallel channels as well. So at IMEC, we've been building these types of silicon neural probes for almost 10 years now. And the way it conceptually works is we start from a standard CMOS wafer. So this really is one single chip. It's a CMOS chip, just in a very unusual shape. And you recognize some kind of needle-like structure. We call it the shank. And on the shank, it's very small, so typically a few tens of micron wide, very thin as well, only a few tens of micron thin. And the reason why it has to be so narrow and thin is because this is being pushed into the brain tissue, and you want to minimize tissue damage. On the shank, or the needle-like structure, you deposit a whole array of biocompatible electrodes that are basically going to provide your electrical interface to the tissue, and that are going to pick up that electrical signal. And then you need to have basically means of amplifying, filtering, and digitizing all of those signals. Those electronics are still too big to fit into the needle-like structure. And so currently we fit them into what we call the base, which is still reasonably small, but it stays outside of the brain tissue itself. And this allows you to actually have a fairly small, simple digital interface. So you don't need to route out a huge amount of cables. And that's the basic concept behind these silicon neural probes. So you can see a bit of specifications here. I've already mentioned the requirement of this shank to be small. It's because you want to reduce the tissue damage. The electrode sizes and pitch are dictated by physiology. Basically, you want to match individual neural cell dimensions. And then the backend amplification, digital filtering, etc. The biggest concern here is, on the one hand, sufficiently low noise. So it depends a little bit which frequency bands you're looking after, but you have to think in the microvolt RMS range of noise. Typical ADC resolutions are 10 to 12 bits per channel. And of course, because we want to record hundreds to thousands of these channels in parallel, we need to minimize area and power consumption per channel in order to not heat up this chip too large, because it is in close proximity to the neural tissue, and you don't want to heat up the tissue because then the tissue dies. So those are the design challenges. I'm not going to go too much into the electronics. If you're interested, I'm definitely interested to discuss this more offline. But I want to focus a bit more on how do we get to these peculiar type of chips. So they do start off as a standard CMOS wafer. The whole CMOS wafer is processed in a standard foundry technology. So all of the electronics and the routing, etc., it's all standard CMOS technology. But then these wafers, they come to our IMEC fab, where we do, where we've developed various types of post-processing flows. And one involves to basically, through a process of back grinding and back etching, define this very thin and needle-like structure. As you can see here, we keep the base structure itself reasonably thick, in this case around 400 micrometers thick, because that provides mechanical stability. But the needle itself is only 22 micrometers thick. And that requires a lot of challenging process flows, because these are very long shanks. You can see this is an example of 1 centimeter. We've actually built shanks of 5 centimeters long. So your silicon becomes reasonably flexible at those scales. It's almost like a thread. But it's very challenging because you still want to have sufficient planar structures, because these needles are being pushed into the brain tissue. Up front, the neuroscientists determine where they want to end up, in which region of the brain, and they need to be there with a reasonable accuracy. If your needle, due to the stresses, is completely bent, for example, the insertion process becomes very challenging, as well as if you record at a completely different part of the brain than what you intend to. So you need to develop all kinds of stress compensating structures to avoid the bending of the structure due to stress. And then the final processing that we had to develop is developing biocompatible electrodes that have a sufficiently good electrical properties, which essentially means they should have a low impedance in the bandwidth you're interested in as well. The current ones that we're showing here are probes that are only required to record. Once you want to add electrical stimulation, the challenges on the electrodes become even much more challenging, because you need to take current density into account, you need to take voltage compliance into account as well. It doesn't stop with the silicon neural probes alone, of course. Our mission was to develop the most advanced tools and put them in the hands of neuroscientific labs across the world. And that is not just a chip. You really need to think about a complete system that neuroscientific labs can make use of in their own environment. So we had to develop this full system for primarily rodent experiments. And the way it works is roughly shown here. So these are very lightweight systems because typically rodents cannot carry more than a few grams on their head. Which also, and you have to get all of that data out. So this thing generates more than 200 megabits per second of data for recording almost 400 channels. We have other versions that can record more channels, and the data obviously scales. So getting that data out reliably without imposing more than 2, 3, 4 grams on the rodent's head is quite challenging as well. So we've built this full system that can actually be fully tethered for power and communication to a readout system as well through a very long 5-meter long microcoaxial cable, which is long enough to run in most typical cages experiments with awake animals. So what can we do with this system? Well, it is today deployed in quite a lot of neuroscientific labs. And basically, you can see here an older experiment, which was published in Nature in 2017 with one of our probes, where you can see how the system is really implemented, how neuroscientists can do awake animal studies as well as head-fixed type of studies. And you can see here that it really generates a tremendous amount of data, too much actually to show on a single slide. So here you can see all of these raw recorded signals only from a very small piece of the shank. So you have to imagine that they get this from these type of traces all along the shank. And then, of course, we enter the domain of neuroscience. What can neuroscientists do with this? Well, they have developed very powerful software to do spike sorting. They can figure out which signals correspond to which type of neuron from which neuron. They can measure propagation from one neuron to the other by doing all sorts of offline analysis on these signals. And if we would take back that curve that I showed at the start of my presentation, you can actually see that these silicon neural probes are breaking that trend, and we really are entering a new region in this Moore's law of neuroscience, where we can leverage the power that CMOS scaling is giving us to really tap into the network of the brain. Now, I want to probably speed up a little bit here. While I've shown this technology to be used in the central nervous system to record from the brain, it's actually very, very relevant for the peripheral nervous system as well, because our peripheral nervous system, from an electrical point of view, looks very, very similar to what's happening in our central nervous system. So we've deployed this technology also in other projects where we basically want to tap into this peripheral nervous system. For example, amputees or prosthetics, to make them smarter and record intention to control a mechanical prosthetic directly through by recording from the peripheral nervous system. But you can do this in 2 ways as well, and you can think of actually stimulating the peripheral nervous system to instill a sense of haptic feedback as well. So we've basically built a similar type of chip here, but this time in a different form factor, where the idea was that we put this chip, which has, again, recording channels, but now also stimulation channels, It's a different form factor because it was intended to be pushed into a peripheral nerve. And thanks to the power of CMOS scaling, we can actually develop these stimulation and recording electrodes to the scale where you can, inside a fascicle, actually target individual neural fibers as well, which could leverage, which could potentially lead to much more precise control as well as much more precise haptic feedback as well. In the interest of time, I'll skip the details on the electronics. Again, it is quite similar. What's also very interesting here is that we had to develop a extremely thin and conformal, but still biocompatible packaging technology as well, to ensure that when we bring these chips into the nerves itself, that we do not impose biotoxicity. Then, of course, this is extremely interesting work, and we can think and conceive of keeping scaling that technology up, and that's actually what the field is really very actively doing. So looking into ever more smaller readout structures, even moving that big base electronics, trying to move it into the shank electronics, etc. And as we progress there, in making the readout electronics smaller and smaller, eventually we'll hit another brick wall. And that is, as we record from more and more channels, obviously we're generating more and more data. So basically, that is most likely going to be the next bottleneck here. As we keep scaling down, how are we ever going to get that data off the system, off the chip, in a power effective manner? So I've already mentioned to you, if we want to think about 10,000 channels, all of the raw data would generate at least 3 gigabits per second of data. So how do you get that off such a small miniature chip which has a very limited power budget? How do you transfer that data to an offline system? How do you even analyze that data? And there, one of the ideas is, right now, neuroscientists really like to get all of the raw recorded data, but they obviously are doing signal processing on that data. And the most fundamental signal processing they do is they identify the spikes, and they extract specific features of a spike so they can actually allocate, based on the shape and the features, spikes to certain neurons, and they can follow the signal propagation through the network. And a very active domain in this research domain, this whole field, is to basically look at how we can move that kind of pattern detection type of signal processing into the chip, right into the front end, to reduce the data that you have to transmit downstream. And of course, that's a trade-off. You have to figure out how much processing power you need versus how much transmission power. But clearly, going forward, that trade-off is definitely going to push some of that signal processing into the chip as well. So it is, next to the technology and purely the circuit innovations, is becoming a big data problem as well. And we definitely anticipate we'll see more and more AI on the edge, or small machine learning type of concepts being integrated to reduce that data bottleneck. So with that, I want to conclude my presentation. I talked about that Moore's Law in neuroscience and how we are really, in the last 4 or 5 years, seeing a significant break in the trend that has been there for a few decades. So I think it's a very, very exciting time. We also see more and more big names jump into this domain. But still, there's a lot of challenges remaining, and it's a field which really requires multidisciplinary innovation based on, signal processing, machine learning, analog front-end circuit design, technology innovation, as well as material innovation. So with that, I want to conclude my talk. Thank you for your attention. And if there's any questions, I'm happy to answer those.
Thanks so much, Nick. Let's thank the speaker. There's time for one or two questions before we go for a lunch break. So there's one question from Jeroen.
Hi, Nick. Jeroen here from University of Antwerp. Very interesting talk. I had a question, since this is a workshop on nanotechnology, and the technology you showed is at the moment quite invasive. You have to put needles into the brain or the human body for the haptic feedback approach. Do you envision a way that the nanotechnology could help to reduce the invasiveness of this kinds of neural probes, or come up with new ways to measure brain activity that are less invasive but also highly accurate?
Yeah, it's a good question, and it really depends on what you require. So most of my story was centered on helping to understand at a fundamental level how the brain operates, and that requires that you reach that individual neural cell resolution. The most straightforward approach is by bringing your electrodes close. There are other techniques, however, that really try through either optical or electromagnetic means or ultrasound means record individual neural activity without bringing an electrode physically close. So that's a domain I haven't talked about. It is a domain that is active in research, and it is definitely one that could lead to a less invasive approach. It's today less mature, but there's definitely potential there. Then the whole area that I didn't discuss about going towards therapeutics, diagnostics, and brain-machine interfaces, definitely there will be technology required that is far less invasive. These neural probes are not going to be the answer or will not be a therapeutic or diagnostic device, let alone a brain-machine interface. Nobody is going to put such a needle in their brain to control their environment. So I think other technologies will be required there, but at that level, it's far less likely that you will need cellular information. So I think this is a segue into advancing the field, helping understand what will be required for proper diagnostics and proper therapeutics. And certainly for brain-machine interfacing. And most likely there you will find less invasive technology that can operate at cubic millimeter to cubic centimeter type of scale and not individual neural scale. We still need new technology that doesn't exist today for those applications. We need to go beyond centimeter scale resolution than what can be achieved with ECOG or with EEG. With a much higher temporal resolution than MRI. So I definitely believe there's opportunities to play at all of those levels for nanotechnology.
Any other question? I think, yeah, Amit, please, feel free.
So thank you very much for interesting talk. I am Hamid from Oslo University Hospital. So we heard about the recording of, from the neurons. So what is the technology now about changing the cellular functions of neurons? Maybe from the external stimuli, or maybe the disordered cellular functions at the neurons. What is the current technology in this field?
Yes, also a very good question. So I only very briefly mentioned about stimulation. So when we talk about stimulation, there's multiple ways you can actually stimulate neural tissue or neural cells. You can do it electrically, which is what we are able to incorporate into these probes. Essentially, it's you push a current into the tissue, and you can either inhibit or enforce a neuron firing like that. So that's electrical stimulation. It's again something that's the most straightforward to implement in these type of neural probes. We are doing that as well. Purely from a technological point of view, there's other ways of doing it as well. There's a lot of research going into optical stimulation, so purely shining light. That most of the time requires genetic modification. So you can genetically modify neurons to have photoreceptors or become photosensitive. Again, it works in both ways. You can genetically modify neuron cells to either be triggered to stimulate or prevent stimulation under when you shine light of specific wavelength into the cells. It's a domain called optogenetics. It's very active. It is very interesting for fundamental neuroscience as well. It does require genetically modifying your tissue. So that limits the applicability somewhat. And then there is the whole domain of non-invasive electrical or magnetic stimulation. And I believe that has the most potential towards, again, therapeutic devices. There's research going on to figure out how non-invasive electrical or magnetic stimulation, for example, can improve neuroplasticity, which would be a very promising early therapeutic technology to delay the onset of certain neurodegenerative diseases there. Again, many different types of technologies. I haven't mentioned even ultrasound. There's also a lot of ultrasound-based stimulation being researched. It's a very complex field, and each of these different technologies has their place and merit in the application space.
Thank you for your answer.
Thanks so much, Nick, for your presentation. So with that question, we can conclude the session. Thank you very much, Nick, again.
Thank you.
So now we're gonna go on a lunch break, but although we have delays, we'll go back to 2 p.m. UTC. So yeah, see you later.
Okay, bye.
Perhaps now. Yeah, perhaps now.
Okay.
Can you try it, please?
Hello, can you hear me? Hello?
Yes, we can hear you.
No?
I don't think it's working.
Let me try with
Can you hear me?
But this one is off. It's weird after every break, it stops working.
Can you hear me?
You're hosting the session, right?
Yes.
Okay, so you have the idea of the session,
What do
just
you
to
mean?
log in.
Sorry?
You have the idea of the Zoom session.
It's room 3.
Okay.
Chat messages, Philip and Zoom.
Yeah, I'm writing to him. They can hear us.
They can hear?
They can hear us,
It's
but
just
this thing doesn't work.
Ah, okay, so this is okay, but that's that.
But it's not even powered on because the light is not on. So before it was working, now it's not. Normally there's a light here.
Yes.
Maybe you pull out any power cable?
Yes, it's that. See that?
Aquí. Yeah. There was a need
O microfone já está, mas agora mas a coluna não.
No, ya lo miramos, ya trocamos,
Ah, já está. Ask him to...
Georgios, can you try to say something?
Yes, can you hear me? Can you hear me?
You have to put it on line. Yeah.
Mute.
Can you ask them again to say something, Philip?
Can you please say something again?
Yes, can you hear me now?
No, it seems we cannot hear you here in person yet.
Ah, sorry. Sì, 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 ma sì. Pode ser aí? Aí está. Ok. E o microfone? O microfone já estava.
Tá? The microphone works. The microphone works.
Então, can you speak again?
Sure.
Georgios, can you please say something again?
Can you hear me now?
Through there. It's the wrong.
It seems we were gonna fix the issue very.
Ask him to do speak, please.
Okay.
Yes.
Okay, now it should work. Can you please say something again?
Can you hear me now?
Well,
perhaps the line is not working.
You can do it through there if you turn on the volume. It's
If we connect directly from here to there.
I'll do.
Can you please speak? Keep speaking, please.
Yes, can you hear me now?
There's something wrong with the cable.
No, not. Try again, please. I'm sorry.
Can you hear me?
Can you please repeat?
Can you hear me?
The connection is not good. You can play through here. You just turn up the volume. People will hear.
Yükseltemezsin.
Can you say something?
Can you please say something again?
Can you hear me now?
Yes, we can hear you now, I think.
Okay. Shall I start?
Yeah. Can you please try to put your slides? Can you share your slides?
Yes.
Thank you.
We don't hear how to move a bit closer.
Do I have to do something for his slides? No.
Well, you can stop sharing your screen. You have to
Can you share the screen?
remove the share. You are showing your.
Will you stop sharing? Yes.
And then you have to.
Can you share my screen?
You have to. Yes. One second.
Okay.
This one you have to use a PowerPoint presentation. Yes, you can start. It's fine. You know, you have to.
Okay. I'm Giorgos Ratidakis from University of Piraeus, and I will present our work on analytical framework for a configured intelligent services placement and mobile user environment. There is interplay between the antenna gain of the X point and the position of the X point and the user equipment in terms of the array's placement. Therefore, there is a need to study the optimal array's placement in a mobile user environment for multiple X point positions and with the use of tunable antennas. We have a downlink T-band system with one arrays, one X point and one user equipment, both equipped with directional antennas. We assume that there is no misalignment, but the direct link is blocked. To estimate the received power, we use a closed form creation from our work, analytical performance assessment of beamforming efficiency in the configured intelligent service-aided links. This expression only works for infinitely large arrays. And the expression the marks the transition from the near to the far field of the array's beam, and is also the arrays to the user equipment distance at which the maximum power is achieved. WRS is the radius of the beam of the X point, of the footprint of the beam of the X point, and the arrays. By infinitely large, we mean that the footprint of the X point beam on the arrays is smaller than the arrays. So we don't mean that it's very large, only that the footprint of the X point beam of the arrays is smaller than the arrays. When this is the case, the received power is independent of the position of the X point, and we can directly estimate the maximum received power. In the simulations, the central frequency is 150 GHz, the transmit power is 30 dBm. The antenna gain of the user equipment is 20 dB, and the room is 4 by 5 square meters. The X point, the arrays, and the user equipment are all on the same plane, and the spacing between the elements of the arrays is lambda over 5. We studied two cases, one with a fixed user equipment position and one with a mobile user equipment. For the case with a fixed user equipment position, we show 4 placements for the arrays. We increase antenna gain of the X point from 30 to 60 dB. With a low antenna gain, the maximum received power is achieved with an array that is closer to the X point. In this case, array is 1. While with a high antenna gain, it is achieved with an array that is closer to the user equipment, which is array 3. The maximum received power overall is achieved with array 3 and requires an antenna gain of 53 dB. For a mobile user equipment, we study 4 scenarios for the placement of the X point. In the first scenario, the X point is placed at the bottom left corner of the room. The second is placed at the center of the left wall, and the third at the center of the bottom wall, and then the fourth in the middle of the room. The user equipment moves freely inside the room. The optimal antenna gain is used, and therefore the maximum received power is achieved in all scenarios. The selection of the array's position is based on a received power threshold, and by increasing this threshold, the number of array's positions that satisfy it is reduced. On the other hand, with a low threshold, we can choose, on the other hand, with a low threshold, we can choose from multiple positions for the array's placement. But with a high threshold, there are only 1 or 2 positions to choose from. Here, for the same positions for the X point, we find the optimal array's placement and record the minimum received power they achieve for multiple antenna gains and the optimal antenna gain. The minimum received power serves as a threshold. The optimal array's placement depends on the antenna gain, the shape of the room, and the position of the X point. For a relatively low antenna gain, for example, 30 dB, the optimal placement is close to the X point. And on the other hand, for high antenna gains, 40 to 60 dB in these scenarios, and also with the optimized antenna gain, the optimal placement is close to the user equipment. The threshold with optimized antenna gain is independent of the position of the X point. So we can see that with optimized antenna gain, the threshold for all scenarios is the same, while with a fixed antenna gain, it changes according to the position of the X point and the RIS. Here we see the difference of using the optimized antenna gain of the X point with using a fixed and high antenna gain. The RIS is placed at the center of the right wall. The left upper figure shows the received power with the optimized antenna gain, and the bottom figure with an antenna gain of 60 dB. The scenario with a fixed antenna gain performs well long close to the RIS. This is the bottom figure. And in most parts of the room, the received power is close to 0 dBm. With the optimized antenna gain, the received power is close to 7 dBm. Yes, the right figure shows the difference between these 2 scenarios. We can see that the difference is close to the RIS, as the optimized antenna gain is high there, close to 6 dB. And the difference is low when the user equipment is far from the RIS, where the optimized antenna gain is low. The figures show the power improvement of the optimized over fixed access point antenna gains. The color map has been saturated 10 dB to emphasize the improvement. And at the top panel, the maximum received power difference is 18 dB. With relatively low antenna gain, the power improvement is increased. When the user equipment is close to the RIS, with high antenna gain, the power improvement is increased with the user equipment is away from the RIS. With intermediate antenna gain, the power improvement is increased in the vicinity of the RIS. In conclusion, we used an analytical model to study the optimal array's placement for tunable and non-tunable X-point antenna gain in a mobile user environment. The optimal array's placement we studied with respect to the X-point antenna gain, the available positions of the X-point and the array's placement, for the level of position for expanded arrays, meaning that contact point is placed at one corner. So the arrays cannot be placed at the adjacent walls. We saw the small arrays placement was also studied with a minimum desired power levels at the user equipment. Because shown that for a fixed user equipment position, there is a single solution. On the other hand, for a mobile user equipment, there are many solutions, but their number is reduced when the threshold is increased. Finally, when the point is close to the arrays, a long time again is suitable, and when the user equipment is close to the arrays, a fine time again is more suitable. Thank you for listening. Are there any questions?
Thank you, Georgios. First of all, apologies for the technical issues that we've had. So I didn't get a chance to introduce you. So I'm going to introduce you now. So the speaker of this presentation was Georgios Trakidakis, who was born in Athens in Greece in 1990. He received his bachelor's degree in telecommunications engineering from the Department of Telecommunications Science and Technology, University of Peloponnese, University of Piraeus, in 2016, and the master's degree in digital communications and networks from the Department of Digital Systems, University of Piraeus, 2018. Currently, he is pursuing a PhD in wireless communications at the University of Piraeus, where he conducts research in the area of wireless communication. So, thank you very much for your talk. Do we have some questions here from the audience? Yes, Jeroen, please go on.
Hi, Georgios, very interesting work. I'm Jeroen from University of Antwerp. I was wondering, so you showed this antenna gain for, I think, the scenario with the mobile UEs, and it's quite variable through the room. It's not like in some places it's good, in others not. Is that something you could fix by placing multiple RIS structures in the room at different places, or do you see another solution to make this, the performance more uniform across the room?
Yes, it can be, the performance can be increased by employing more RISs, but the study goes with one RIS only, to find the optimal location for one RIS.
Okay, thank you. Do we have any other questions? I do have one. So I was wondering, in finding the optimal position of your intelligent reflective surfaces on the walls of the room, in the framework, do you define kind of discrete locations at which you're searching for the optimal SNR, or is it somehow continuous?
What is discrete?
Thank you.
With a step of 0.5.1 meters specifically.
Okay, thank you, Georgios. Okay, the next presentation is from Razane Abu Ayseh. So please try to connect yourself. I hope that's gonna work. Let me tell you for a few. Razane Abu Ayseh is a CIFRE PhD student associated with Nokia Bell Labs and INRIA France, INRIA Paris. She received her master's degree in embedded digital systems in 2017 and her bachelor's degree in electronic engineering in 2016 from the University of Sussex in the UK. Her research focuses on multi-robot cooperation and coordination. Just try it.
Is my yeah.
Yeah, but you first need to go to full screen, and then we need to share your screen in Zoom.
So should I go Zoom first and then?
No, first full screen, and then we share the. Yeah.
And then start my video, or?
No, share screen, and you have to share the full screen thing. That's here, I think. Yeah. Share.
And then
Also, please start my video.
Yeah. Yes.
Okay.
Now you can start.
All well? There's videos, so how do I play the?
Oh, you just you're in the video mode. No, you're in.
There we go. So I just click on that. That's fine.
Yeah, you mean button.
Okay. Oh, sorry. Hi, everyone. I'm Rosanna Boisha, and I will be talking to you today about my work on coordinating a swarm of micro robots under lossy communication. This work was also done in collaboration with my supervisors, Francisco, Mediana, Lou, and Thomas. So I'll give you a little bit of introduction on the topic and the area of our work. So overall, we envision having a swarm of multiple small millimeter scale microrobots to be able to carry out critical missions such as exploration and mapping, for example, for hazard detection or for localizing victims in post-disaster environments. Now, what all these missions have in common is the need to reach full coverage of a certain area, which is unknown to the robots previously. And since all these missions are quite critical and there's human lives involved, the main objective that we have is to minimize the time to completion. And when we have like a bunch of robots and we want to minimize the time to completion, one important aspect is for the robots to be able to communicate with each other to achieve this collaboration. But one issue in previous work is that communication isn't often taken into consideration when designing such algorithms. So communication is either always assumed to be perfect, or there is just assumed to be a very binary condition where either there's full communication or there is no communication at all. And of course, perfect communications as such do not really reflect real world conditions where there are certain things that can affect the packet delivery ratio, such as interference or path loss, or etc. So I'm going to start and just give kind of like a wider context and vision and introduction to what the team does in general. So we are working on these little swarm robotics called the dogbots. And they're very simple robots. You can actually put them together yourself and assemble them. And the idea is to have like small robots, but to have a large number of these robots that can collaborate together. And you can control them from your phone or from a central entity. It's fully open source, the firmware and the software that comes with it. And other members of the team are working on localization of these robots. And we actually got to introduce these robots to the robotic community 2 weeks ago at MRS, which was super cool to get to see how relevant this is to everyone in the robotics community and how they interacted with it. And now as a team, like my side of things lies into the actual algorithms for the robots. And we have since we still don't have the full testbed of robots, what we are doing is we are working on simulating these algorithms. And that is what I'm going to get into right now. Yeah. So overall, the objectives of this work. So as I mentioned, in robotic swarm exploration, communication is usually simplified. So what we want to do, our objective was to develop and validate a packet loss tolerant mapping algorithm that reliably completes all of the time, and to evaluate the impact of packet loss on the time it takes to complete the mapping task. So I'm going to start with the communication protocol. So we assume we have a certain number of robots, and we have an orchestrator with which is a centralized entity that controls these robots. And every second, this orchestrator sends a command down to all of the robots to give them updated movement instructions. However, not all of the robots report back constantly. What happens is when a certain event happens, now this event varies based on the algorithm, when a certain event happens, only those robots that had an event triggered would report back to the orchestrator and send back a notification requesting a new instruction. Otherwise, they continue going in the same direction. So then the orchestrator updates the movement, and then when the next command is due, it contains the new movement instructions for those robots that requested it. Now, what happens if, let's say, this packet didn't actually reach the robot? What happens is the robot just keeps retransmitting this packet every second. So it keeps sending a notification out every second until it finally hears back from the orchestrator with an updated movement. Yeah. So that is basically how the algorithm becomes robust to packet loss. And then for the exploration and mapping side of things, initially, the environment is fully unknown to the robots. So all of the cells are considered unexplored cells. And then to simplify, I'm going to just explain for one robot how this is done. So if you have like a robot is set in its initial position, once it's inside a cell, this cell is considered to be an open cell because there is no obstacle there. And then since we're using frontier-based exploration, all of the cells that are one step away from the cell where the robot is and have not been explored yet are all potential targets for the robot to move to. Now, the closest one out of these cells to the starting cell is selected as the next position, and then the robot goes there, and then and this keeps going on. Now, if the robot bumps into an obstacle, then that cell is marked as an obstacle cell. And what happens is the robot, this is what we consider an event in this algorithm. So when the robot bumps into an obstacle, it sends back a notification to the central entity just saying, hey, I bumped. And then the central entity knows where it is, and then it just puts a dot on the map. And then the more dots you have, every time these dots are a certain distance apart from each other, they connect into a line. And then when you have a bunch of lines that are close enough to each other, they get connected into one big line, and then the dots are removed. And then this keeps happening until there are no dots remaining and all of the lines are connected to each other. And that triggers that the map has been complete. Now, so why we did all of this? So what we did was we simulated the behavior of a swarm of 50 robots exploring and mapping a 80 by 21 meter squared environment with our algorithm that I just explained, using our open source simulator, which I showed at the very beginning in the video, and it can be found on GitHub at this link. And what we want to do is we want to kind of like see the effect of various packet losses on the algorithm and the performance. So we run simulations with 10 flat PDR rates across any point in the environment from 0.1 all the way to 1. So 0.1, 0.2, 0.3, all the way up to 1. And then what we can see here is that we can see the massive effect of PDR on the actual time to completion. So we can see here with the same algorithm with a packet delivery ratio of 1, which means all of the packets go through all of the time. We can see it's the number of cells being discovered are quite steady, it's quite linear, and it completes in a rational amount of time. And then as the PDR starts to go down, it's still acceptable to a certain rate. But then when you start to go to 0.5, for example, it's the time it takes to complete mapping has more than doubled. And then as it gets lower and lower, and then you see a worst case scenario, for example, you have 0.1, the time it takes to complete mapping goes up to hours. And if we are in a critical mission where we are trying, for example, to find victims, this extra time it takes could literally cost lives. And the main takeaway that we are trying to deliver here is the importance of considering more realistic networking conditions when designing any algorithms that involve robotic collaboration, coordination for critical missions. Now, our future work is to kind of like incorporate context of network connectivity into the logic of our algorithms in the first place. So now that we know how much of an impact network conditions can have on the actual behavior of the robots and the performance of the mission, what if from the beginning the algorithm was designed in a way where we could exploit our understanding of the networking condition in an environment, and we can kind of like build that into the algorithm from the first place, so that we can end up with an algorithm that performs well despite all of these losses. We also want to work more on including non-ideal headings and speeds and localization in our simulator. And we are also currently working on experimentally validating our work, and therefore building a swarm of 1,000 robots, which I showed at the very beginning in the video. So yeah, so thank you for listening, and I'm happy to take any questions. I went a bit quicker.
Thank you, Razan. Do we have any questions from the audience? Please, Sergi, go on.
So thanks for the talk, it was very interesting. So can you elaborate a bit more on the loss model? So the packets they could just randomly get lost no matter where the phone is, or no matter what the property?
So
give me just 2 seconds.
Yeah.
So the question is if you could elaborate a bit more on the loss model. Is that correct?
Okay. Yeah. So we actually used 2 loss models, but the first thing that we did is we assumed, so we did various tests, and each one with a fixed packet delivery ratio. So let's say that we have a packet delivery ratio of 0.9. We assume that 90% of the time the packets are going to go through. So we just have a random generator that kind of like, based on that probability, there would either be a packet that's generated that's perceived or not on the other side. But that was so that we can kind of like test with different specific PDRs, so we could show the worst case scenarios. Now, another model which we used is takes RSSI into consideration and the distance between the central controller and the robots. So technically, as the robots get further and further away, the packet loss would increase.
Yeah, that's what I was thinking, right?
Yeah.
The losses will be first in some sense, right? At
some
point, you will lose communication, and until much later you will not gain it. So I was wondering if the anchor has to be fixed, or you can move also to try to, I don't know, be in a position that everyone can see it and so on, or if you thought about relaying through other robots that are, I don't know.
Should I repeat? Okay, so you just asked me about, for example, if the main orchestrator has to be anchored, or like if we can add some sort of relay points for the communication. And that is actually exactly what we are working on right now. So right now we are working on like some of the robots at some points being triggered to stop exploring and become relay robots. So what we're working on is which robots should become relays, where should they be positioned, and how can they kind of like, how can they be positioned in a most optimal way to kind of like enhance the network connectivity.
Excellent.
Yeah, go on.
Do you have a specific communication model? So like specific channel model and fading and modulation scheme, or is it just the package arrives or not with a certain probability? So
okay, so he asked me about if we have certain like communication models like for fading and like how we determine whether the packet goes through or not. So we used so yeah, for the first one where I said like which was very standard, yes, we just were like, okay, this is the PDR, it's 0.1, it's 0.2, and then based on that, the packet either goes through or not. But now we are looking into different models, which, as I say, take RSSI into consideration, and we've found previous papers which already like map the RSSI to the PDR. So we haven't done that exact work ourselves on finding like what the RSSI values would be based on the location of the robot and based on the obstacles. But we took the PDR table from previous work that just maps RSSI to distance and then that to the PDR. So mostly right now it is distance, but it was validated by other people in like real world experiments, and that's where the values come from. That makes sense.
Yeah, one question a bit related. Now you consider like a centralized approach where the controller can just tasks to the robots, but in swarm intelligence, a lot of work is also on fully distributed approaches where robots only communicate with their neighbors to kind of explore the area. Have you considered something like that? Or?
He just asked about centralization and because most swarm logic actually looks into decentralized logic. So he was asking if we are looking into more decentralized algorithms. So the reason we went for centralized in the first place was two things. One thing was we wanted to have one place that has the map at all times. And we wanted to make sure that the map that was being built was consistent all the time. And now if you want to add distributed logic, there's a lot of problems that can come with that in terms of like you can have parts of the map that don't kind of add up correctly, or you can have robots that don't have all of the knowledge and so on. And the second thing is because we are assuming for like the long-term vision for this to be used for critical missions, you do usually end up having certain rescuers that are at a base station or somewhere which need to hear back from all of the robots all the time. So we decided to kind of like use those two things to build, to focus on centralized algorithms. So we are not yet looking into decentralized, but I am aware that that is probably a direction that we could take in the future.
Okay, do we have any other questions from the audience? Do we have time? There is 4 more minutes, yes. So I do have one question, but Sergey, go on first, please.
So, simulator or whatever you're using, is there any way to track the power consumption of the robots? Like how much is taken to move, how much is taken to communicate, and how much is taken to localize, and things like that? Is there any information related to that? So I'm thinking this is NanoCoCoA, so good thinking, at least I'm thinking how to downscale that into applications that might require to have robots which are already energy constrained. I don't know, to explore a fracture of the axe or something that requires more robots, right? So I'm interested in knowing how much power is invested in everything so that we can try to optimize it. Do you have that information?
Okay, so the question is if in the Atlas simulator you can model the power consumption of the robots or different tasks that the robots perform.
Yep. So currently that is not a feature that we have in the in our simulator. But yeah, what you said is very accurate. Like in the end, we do want to downscale these robots to become smaller and smaller, and then energy will become an issue. So I think that since our simulator is fully open source, this is a feature that can be added, and that's definitely something very interesting to look into for the future.
Can we? Yes. No, there were no questions. No, from the remote audience. So let's thank the presenter. Thank you so much.
I just take the thing out.
Yes, feel free to. Okay, the next talk is from Avik Booz and Prasun Gosal, and the title of the paper is Dynamic Application Mapping on CTH Network, a Performance-Centric Approach. And the presenter, Avik Booz, is currently associated with the Indian Institute of Engineering, Science and Technology in Shibur, India, and a research fellow and working on energy and performance-centric design of 3D networks on chip. He has received his master's degree from BESU, Shibur, India, and bachelor's degree from WBUT in India. Avik, the floor is yours.
Thank you, sir. Okay. Good afternoon, esteemed speakers and authors and esteemed host. Today I'm presenting Dynamic Application Mapping on CTH Network, a performance-centric approach. My other author is Dr. Prasun Gosal from University Department of Information Technology, Indian Institute of Engineering, Science and Technology, University, Shibur, India. So this is the brief roadmap of the presentation. First, we talk about the topology itself, then we come to the mapping, Now, there are two kinds of what is a mapping, if I want to explain. So after in a computing system with more than one processors, many core processor system, if an application comes and asks the operating system to deploy it on the on its threads on the different processing cores, then the job of application mapping comes into the picture. There are two kind of application mapping that has been exercising. One is static, that is before the system goes up at the design time, it is defined what are the application which are going to be executed on that system. And so it is much more mathematical before at the time of design of the system, but it lacks the generality. But in case of dynamic application mapping, whenever an application may come and asks the operating system to deploy it on the processing cores, assign its threads different processing cores, and the application and the OS system has to do that. So this dynamic nature of the application mapping actually gaining more and more popularity recently, because it reflects the generic architecture of the system, how a computing system works. So this is a brief history how network on chip come into the picture, replacing the traditional bus-based system. And these are the various research field in NOC. So we are focusing on dynamic application modeling. So an application have multiple threads or processes. So those threads are an application is represented as application task graph. The different threads of executions are represented with nodes, whereas the communication is represented by the edges. A directed edge Eij I, j connects a communication task pair Ti and Tj. The weight of the edge is the volume of the data exchange between those tasks which are assigned to some processing cores on the NOC floor. A task is characterized by its arrival time, execution time, and its deadline. And also, the NOC itself is perceived as a graph. Before assigning task onto the NOC, it remains as an undirected graph. A core graph ng equal to n comma c expresses an NOC topology where n represent the set of vertices. That means the set of IP cores, cache memory blocks on the network, and C is the channels, physical channels. Okay, then the edge weight Wij in the NOC core graph is the communication volume after assigning some threads on those computing cores. And the maximum data rate a channel Bij that a channel can offer is called the bandwidth of the channel. Now comes the mapping. A mapping algorithm take care the job of a mapping algorithm is to map the different tasks on the NOC NOC IP cores. And after successful mapping, the OS prepares a scheduling assigning each task a start time. A successful schedule preserves these conditions where the start time is always greater than the arrival time of the application, and the finish time f of Ti of task Ti is actually the start time plus the execution time of the tasks, and a task the finish time of a task cannot exceed the deadline. Now here comes the mapping cost in terms of communication energy and latency. To measure the communication energy for a particular application task graph, for every pair of communicating nodes, we need to track the total number of packets, which are eta packets, which is exchanged between two IP cores or two tasks Ni, Nj, and for each hop it traverses through the network, the routing computation delay, the processing energy in the router, which comprises the routing computation delay, VC arbitration delay, and switch delay, and the crossbar delay, and also propagating the packet through the physical channel also of length L. The length is L, between a router from kth stage and k+1 stage. These also need to be accounted to measure the total energy of an application, of executing an application and its mapping. And here is the network latency of a packet. If the packet traverses an average h ni, nj hops, ni, nj, that means the packet is going from the node ni to node nj. So for that, the latency become like this. For the packet size in bits, we need to calculate the time required to process the packet for routing computation and VC arbitration, as well as the switch arbitration and crossbar delay, along with the propagation delay through the network, through the channel. So this actually comprises the communication latency. Now, these are the mapping parameters. These are the actual performance parameters related to an application mapping, whether it is static or dynamic. So in case of dynamic application mapping, the deadline satisfaction is more and more important, because at the middle of a task, an OS need to assign some reserve some resource for an application which has come in between of the task. So the deadline satisfaction of the application after mapping, it is very important. And the execution time and the mapping and scheduling time, that means how the algorithm is, how efficient the algorithm is, how lightweight the algorithm is to which executes in a system to map the applications on the NOC. And the placement of task is very important. Some constraints are there, like total energy, communication latency, hop count of communication, and network congestion, which are the constraints which are related to different parameters. Like for example, placement of task, this design challenge actually related to all of the constraints. So design the underlying NOC topology is very crucial in order to extract the best out of a dynamic mapping strategy. So these are the challenges that encircling around an NOC topology design, the underlying topology design, which are scalability, path diversity, bisection width, and power consumption. So these all each and every design challenge is connected to some constraints like network diameter, interconnect length, router radix, and load balancing. For example, if we scale the network diameter gets increased. It may possible that scaling the network results into having long range interconnects also. Router radix could have been increased, and there is load balancing, which is directly connected to bisection width of the network. So designing an NOC topology is a matter of balancing the above design trade-offs in order to improve the performance parameters like communication latency and throughput. So this slide is which I was explaining previously. So I skip it. Now, how important is the topology design regarding an mapping of an application and evaluating its performance? For substantially large application size with significantly large number of cycles in the task graph, that means various the number of communicating pairs if gets high, then online mapping and scheduling becomes much more complex in order to place every pair of communicating tasks on the NOC tiles as near as possible. So it most of the time it results sparse placements of the communicating task. If the tasks are placed sparsely, then their average hop counts of their packet communication becomes greater, which affects its latency, which also comes with greater communication energy. And as a result of that, mapping and scheduling time gets increased, average communication hop increases, communication latency affected, which I was talking, network congestion may occur, execution of the task is increased, task deadline miss rate also may increase, overall energy consumption is increased. Now, the mesh is the most prevalent topologies, out of the most prevalent topologies on which most of the application mapping, either it's static or dynamic, is proposed up to now. So we are actually the experimental phase actually associated with comparing with mesh topology. So with increasing network size of mesh, the diameter increases significantly. For that, communication latency increases significantly with scaling of the network. The effect of load balancing diminishes despite having significant path diversity in mesh due to network congestion. The saturation point converges early. That means in very low network injection rate, injection rate, the network saturates. But these bad effects of dynamic mapping is applications with large number of communicating tasks compels the mapping of the algorithm to place them sparsely on the NOC. As a result of that, overall communication cost increases, mapping and scheduling time increased, considerable number of tasks miss their deadline. Now we come to the dynamic application mapping. So before that, we will discuss the topology itself, why we choose this topology over mesh. Now, as we can see, it's a 8x8 form of the proposed topology, which is cube tree hybrid. As the name suggests, this is a tree, but in this tree there are several cubes. The cubes are formed to actually enhance the reachability from different nodes to the other nodes. And there are some interconnect length issues existed in the prevalent tree-based system like butterfly factory, butterfly itself, and path diversity. All those to handle all those in under one roof, we're keeping in those trade-offs in mind, we designed this topology. And to scale to scale this network, actually we don't scale this tree-based topology in the natural way as other trees can be, like fat tree-based trees can be scaled, because of in case of tree, the experimental observations has proven that in case of tree, if we scale the tree, that means it comes with larger number of levels of the tree. And if we go to the higher levels of the tree, the network injection rate also increases. So to scale this network, this is an unit of scaling of the network. To scale the network beyond 8x8, we need to associate additional trees. So in a particular NOC layer, at most 4 such trees can be accumulated, and they are connected in a specific manner, which is the root level routers, that is this red, green, violet and black routers are connected to that other same colored root routers. That means this red root router is connected to other 3 red root routers of the floor. So this is the floor plan of the topology, which is a 16x16 actually CTH core layer. We are termed it as a core layer because it has the IP cores. So as we talked about the upward bandwidth doubling by traffic load doubling problem of the traditional tree-based system, and for that we have relinquished our design. So, and this is we make this 8x8 as the unit of scalability. For that, this is a 16x16 core layer, and for load balancing we use another kind of layer which doesn't include any IP block, only the router architecture is there. The connectivity and placement of the router is same, but the IP blocks are absent because they are designed, or they are placed in the additional layers, which are called mirror layer, to alleviate the traffic load of the core layer. So this is what I was talking about in the previous slide. And this network comes with the very high bisection width, which is 56. And using the additional core layer, additional mirror layers, the path diversity of the tree is also significantly increases. So this is the various routing scopes of the design, which is the tree. In the tree, there are 2 kinds of regions, these regions and this region. And within a region, there are 8 such localities, like this locality. A locality comprised with a local router, which is a blue colored router, and 4 IP blocks, along with a DTDMA pillar node for 3D communication. So based on the scope, the addressing format of a packet becomes very simple. which is there are if there are m number of layers, so some bits needs to be reserved to specify the layer number of a packet for which it is destined, and to identify the destination tree number, we use 2 bits, because in a layer there are 4 trees. In a tree there are 2 regions, that means 1 bit is sufficient, and in a region there is 8 localities, 3 bit is sufficient for that, and for in a locality there are 4 nodes, that's why 2 bits are there. So benefits of CTH is the diameter of the CTH network is very low, which is 7 for an 8x8 for a 16x16 network. That means for a 256 nodes of an NOC, the diameter is 7, which is significantly low. For the same in case of mesh, which is 30. And also according to the routing algorithm proposed in the CTH previously, the maximum hop count yields in anywhere in the network, which is 10 if we use only the core layer, and if we use 2 or 1 mirror layers, it becomes 12, but not more than that. This uniform hopping characteristics makes the topology very attractive for the application mapping of large application task graphs, where even if there are sparse placement, but the application but the communication hop count does not affect the placement. So in case of in order to devise a mapping strategy, the algorithm is relinquished of the complex calculation of various complex calculation, where we need to think about the nearmost placement of tasks and their parent tasks, etc. The runtime algorithm of mapping becomes simple. The sparse placement of tasks does not affect the latency considerably, and overall performance parameters like allocation time, execution time, deadline satisfaction, and power consumption is significantly higher than CTH network in case of mesh. So this is for a 16x16 network. This is in uniform random traffic. This is the traffic load distribution according to the routing algorithm, which imposes on the various stages routers. So this is a local router where 4 IP blocks are there. Each IP is injecting lambda 0 traffic. So there are 4 lambda 0 traffic. The whole traffic is divided into all of its physical channels. And in every stages of the network, this load balancing divide of the overall load happens in the network. So, and this is the overall load of each router of a 16x16 mesh network, which is 5.79 lambda 0, where each IP block is actually injecting lambda 0 traffic. It is operating as lambda 0 packet injection rate. So we can see from the lowermost layer, that is the local layer of the CTH tree, each local router actually faces the maximum traffic in the network, which is 4 lambda 0. But however, this traffic does not affect the communication latency of the CTH network, as the local router do not take part in the intermediate traffic routing. In spite of that, it is 30.92% less overwhelming than the mesh, the traffic load. For the regional stage of the routers, which is a regional router faces 1.94 lambda 0 traffic in case of CTH, which is 66.49% regarding to the in comparison with the mesh. And for the root level, it is 88.25% less for the mesh. This is quite opposite of the standard tree-based design, because as we used mirror layers for load balancing, and at each stages of the network, each level of the tree, each router divides is half of the traffic to and half sends it to the mirror layers, and half channelized through the core layer. So this is the one reason, and the another reason is, as we restrict the tree to scale like any other generic tree, and make the 8x8 form of the tree the unit of scalability, these two contributes actually this opposite characteristics, where as we go up to the level of the tree, higher level, the traffic load actually reduces. So this is a proposed strategy of the dynamic application mapping. Here we can see the after selecting a task, if when the strategy when the algorithm needs to place the parent task, it only looks for the availability of the node. First, it finds the locality of the already placed tasks. Is there any IP core free? Then if not there, then the region. Then if not, two regions are already filled up, then it looks for the tree of the other three trees of the same layer. If there also the IP cores are already assigned and cannot be given to another thread of the application, then it looks for another core layers, if any. So this strategy actually based on the availability of the nodes. It does not need to look for the nearness of the application, because it remains under a very low diameter, and also the maximum hop count is restricted to a very significantly low hop count. So the application mapping strategy algorithm is relinquishes of those complex calculations, which actually reduces the mapping complexity and the execution time of the application and the scheduling time also, which we find in the next stage, experimental stage. So this is the
Avik, can I interrupt you? Yes.
Yes, sir.
Sorry, you would have to wrap up in say 1 minute or less.
Okay.
Thank you very much.
Okay, so this graph is this application task graph is mapped regarding on our CTH topology using our algorithm, and also the nearest neighbor principle, very basic principle for mesh. And what we can see here, the hop count, 51% of task pair in mesh, actually more than 5 hop count it yields, and 25% of that in mesh become more than 7. But in case of CTH network, it actually not more than 5. Where the higher number of hop count yields, it is not more than 5. It cannot be possible in a 8x8 form of the CTH. This is the attractive nature of the CTH. So these are the results. This is the network configuration. We have used both parsec and synthetic benchmark. Sniper sim we use to generate the traffic traces, and these are the algorithms existing on mesh which we compare. And here are the application performance, where we can see that the in terms of network latency, total energy, and the deadline satisfaction of that overall deadline satisfaction of the tasks, our proposed CTH based application mapping algorithm, dynamic application mapping algorithm, outperforms than the existing mesh based algorithm. So the immediate future will focus on performance testing under the faulty scenario of the network. And this is the previously published paper of CTH, which we can't explain here more in detail. And thank you.
Thank you very much. Very interesting talk. Unfortunately, we don't have time for questions, only if someone has something very rapid to ask. Yes.
More a comment than a question, but have you considered introducing thermal management problems on the mapping? Because generally you try in thermal problems, you try to avoid having many tasks close together because it generates a hotspot. So have you considered with this topology to also have thermal problems?
The question is, have you heard the question?
Yeah. It is regarding the thermal consequence of mapping. Am I right?
The thermal management, if you have considered.
Yeah. What happens? Yeah, what happens if we deploy two threads on two near IP cores side by side? Then the temperature tends to grow. Temperature tends to grow. So we have to avoid, in case of thermal, such that no thermal anomaly can arise. There is already a restriction. We have to separate two placement of a task in a minimum hop distance. So that is the problem in mesh, and this topology actually, as right now, actually we doesn't include that, but the design is actually capable of handling that. We will include that in our future work. Actually, we can, as sparse as possible from the thermal perspective, we can place the application threads, but it won't increase the hop count significantly. sustaining, giving the sustainable performance.
Thank you very much. Serge is also thanking you. He's nodding. He agrees. Okay, thank you very much. We're going to go to the next talk, the last one in the session. So our next presenter is Venkata Sai Praneht Karempudi, and he's going to talk about design exploration and scalability analysis of a CMOS integrated polymorphic nanophotonic arithmetic logic unit. Let me give you a few words about our presenter. Venkata, you can already put your slides. Share your slides.
Am I audible?
We cannot see your slides yet. Okay, Venkata Sai Pranesh is a doctoral student at the Department of Electrical and Computer Engineering at the University of Kentucky in Lexington, Kentucky, USA. He holds a master's degree in electrical engineering from the University of Akron, Ohio, USA. His research interests are silicon photonic interconnects and photonic device modeling.
Can you see my
Venkata, the floor is yours.
Can you see my slideshow?
We can see your slides. Yes, you can start. Thank you.
Okay. So hello and welcome to this presentation on design exploration and scalability analysis of a CMOS integrated polymorphic nanophotonic ALU. My name is Praneeth and I'm a PhD student at the University of Kentucky. So as we know from the famous Moore's law that the number of transistors on a chip get doubled every 2 years. So over the past few decades, transistor size has shrunk down and currently billions of transistors are being integrated on a single chip. So this Moore's law has guided the advancement of computing till date. But unfortunately in recent years, Moore's law has been facing some serious challenges because nanofabrication technology is experiencing physical limitations because of the exceedingly small sizes of transistors. So this has motivated the need for new computing technologies in order to meet the modern computing demands. So silicon photonics has been identified as one such promising technology. It is CMOS compatible and it provides many advantages compared to its electronic counterparts, such as sub-picosecond speeds, low power consumption, low latency, and ability for multiplexing. So currently, silicon photonics is applied in many fields, such as optical interconnects and microwave photonics. But silicon photonics-based optical computing has gained tremendous attention, and several prototypes of silicon photonics-based circuits and ALUs for computing have been introduced. So as we know, an ALU, arithmetic and logic unit, is a fundamental and vital building block of various computing modules. So an ALU can perform many arithmetic and logic functions, and one of the key parts in an ALU is a full adder. So this full adder has two addends and an input carry signal that travels from first bit to the last along the critical path that contributes to the total latency and determines the operating speed of the full adder. So these are the expressions of a full adder circuit that computes sum and an output carry. So in these expressions, A XOR B represents the propagate value of a full adder, whereas A and B represent the generate value of a full adder. So over the past few years, notable efforts have been made to enhance the performance of a full adder circuit by introducing different architectures, and among them conditional sum adder, CSA, has significant importance. So the CSA is one type of a carry select adder that splits an n-bit full adder into x sets of m 1-bit full adders. So it consists of a section of propagate and generate unit on the top that produces propagate and generate values that are fed into the individual full adders. But the problem here is the carry signal between the adjacent sets are unknown before the computing. Therefore, we have two sets of hardware, as you can see here, to generate two sets of outputs based on the assumption that carry signal for each set is 0 and 1, as you observe from the figure. So once we know the incoming carry, we can select the correct set of outputs using mux units without waiting for the carry to propagate through the entire full adder. But the main advantage here is the adoption of these extra full adder circuits that consume more energy and space on the chip. So prior work has significantly enhanced the throughput and the speed of CSA by extending each of the m-bit full adders in CSA into an optical carry propagation network. So this OCPN consists of a network of modulators and directional couplers. So as we can observe from the architecture, we have two electro-optic modulators represented as red and green rectangular boxes, along with 2x2 couplers, which compose 1-bit So we also have two continuous wave input wavelengths, lambda 1 and lambda 2, with different wavelengths that are fed into the circuit. So these wavelengths are encoded with carry signals 1 and 0. And these incoming optical signals are wavelength division multiplex, which means that they go through same structure simultaneously, and two sets of results are calculated independently. So with this eliminates the need for an extra set of full adder circuits, which we have seen in the previous slide. So within each clock cycle, the electrical signals from the PGO on the top are fed into the modulator simultaneously. So all of these carry signals are directed towards this filter, followed by an array of photodetectors here. So from these photodetectors, the decoded electric carry signals are directed towards a network of electronic mux and some generation units. Now, this architecture of OCPN can be used to realize a polymorphic nanophotonic ALU, PONALU. So this OCPN-based architecture can achieve different functionalities at different times. So we can use this same OCPN architecture, and by dynamically changing the combinations of input wavelengths, we can achieve different functionalities such as addition, subtraction, increment, decrement, comparison, which we can observe from this figure. Also, we can cascade multiple OCPNs to achieve various functionalities, as you can observe from this structure, where we can cascade two OCPNs to achieve A plus B with twice the higher bit precision. Therefore, this polymorphic design of an ALU can be used to perform multiple computing operations at high speed with very high hardware utilization, flexibility, and low power consumption. But it is important to see how we can scale this performance of PONALU by taking into account various design factors of PONALU, which is so far unexplored. So therefore, in this work, we carry out a design exploration of PONALU, from which we derive various design guidelines that can help scale the speed and energy efficiency of PONALU even further. So our main goal in this work is to determine how we can scale the performance of PONALUs. So as we saw in the previous slide, PONALU consists of various circuit blocks such as OCPN, PGU, SGU, and MUXU, which we can call them as OMPS circuit blocks. And it is intuitive that throughput, energy efficiency, and the area of PONALU depends on various performance metrics of these OMPS circuit blocks. So we have identified some key performance metrics here of these OMPS circuit blocks. So these performance metrics are affected by various design factors of these OMPS circuit blocks. And it turns out that careful exploration of these design factors play a key role in scaling the performance of PONALUs. So these are some key design factors which we have identified that impact these various performance metrics of the OMPS circuit blocks. So, but the main challenge here is that these performance metrics and design factors of OMPS circuit blocks depend on various design variables which were never identified or explored before with respect to PONALUs. So therefore, in this work towards scaling the performance of PONALUs, we make three main contributions. So our first contribution is the identification of design variables that impact the performance of PONALUs. Our second contribution is the design exploration of these identified design variables. And our final contribution is the derivation of key design guidelines to enhance the performance of PONALUs. So in our first contribution, firstly, we identify the design variables that impact the performance of PONALUs. So if we look at the design variables corresponding to each of the OMPS circuit blocks, starting with the design variable of OCPN here. So silicon photonics technology node that is utilized for implementing electro-optical components in an OCPN controls design factors corresponding to OCPNs such as capacitive loading, operating speed, area, and total optical losses in OCPNs. So other design variables such as bit precision, WDM degree, length, and width of OCPNs, and number of waveguides in an OCPN control the area, speed, and optical losses of OCPNs. So especially the DWDM degree here of OCPNs control the crosstalk and signal truncation related optical losses in OCPNs. So coming to the design variables corresponding to PGU, SGU, and MUXU, here CMOS technology node that is used for implementing these circuit blocks control the capacitive loading, size, and speed of these circuit blocks, whereas clock rate also controls the speed of these circuit blocks. But among these variables, some of them are independent upon which other variables depend. So among design variables corresponding to PGU, XGU, and MUXU here, clock rate depends on the utilized CMOS technology node. Similarly, in order to understand the dependence between design variables of OCPN, let us consider an example OCPN with 5 waveguides. So in this OCPN, there are total of 2M wavelengths corresponding to 2M carry bits, M bits corresponding to input carry of 0, and other M bits corresponding to input carry of 1. Also, this OCPN consists of total of 4M microring modulators, 2M modulators corresponding to the propagation, and 2M modulators corresponding to the generation. So therefore, for a total of J waveguides in an OCPN, we have 2 M by J wavelengths per waveguide, and then we have 4 M by J modulators per waveguide. So based on this nomenclature here, we have derived the equations for length and width of OCPNs. So in these equations, 125 microns is the pitch size between microring modulators, whereas 10 microns is the keep out zone to isolate photonic components from their neighboring structures. So in order to reduce optical scattering and leakage. So among all of these design variables related to OCPNs, SiP technology node, silicon photonics technology node, number of waveguides, and bit precision turn out to be the independent variables upon which other variables depend on. Whereas for the PGU, SGU, and MUXU blocks, CMOS technology node turns out to be the independent variable upon which the clock rate depends. So coming to our second contribution in this work, as a part of design exploration, we have considered specific values for our independent design variables and evaluated a 64-bit Ponalo in terms of various performance metrics shown here. So from this evaluation, we derive new design guidelines that can help in scaling the performance of Ponalo. So these are the silicon photonics and CMOS technology nodes we have considered. Since Ponalo is implemented as a CMOS integrated photonic circuit, we consider these combinations of silicon photonics and CMOS technology nodes in our evaluation on 64-bit Ponalo. So along with SiP and CMOS technology nodes, other independent variables such as number of waveguides and bit precision, we consider power of 2 values between 1 and 64. So for each of the silicon photonics technology nodes, these are various loss and other spectrum parameters corresponding to these technology nodes we have considered for this evaluation. So starting with the area analysis to evaluate area of OCPN blocks of our considered Ponalo. So we have used the equations which we have derived as we saw in the previous slide. Similarly, to evaluate the area of PGU, SGU, and MUXU blocks, we have used the standard cell library and layout rules from prior work for the 45 nanometer SOI technology node, CMOS technology node. So here we have total area for both OCPN block and 64-bit Ponalo for different combinations of bit precision and number of waveguides. So as we can observe from these graphs, the area of OCPN and Ponalo configurations for which bit precision greater than the number of waveguides is less compared to the OCPN and Ponalo configurations for which bit precision is equal to the number of waveguides. So therefore, from this area analysis, the design guideline is that the number of waveguides in Ponalo should be less than its bit precision to improve Ponalo's area efficiency. So the next performance metric we have evaluated is critical path latency. So in Ponalo, since the optical signal traverses through corresponding OCPNs at the speed of light, which has sub-picosecond latencies. So the latencies corresponding to the PGU, SGU, and MUXU have critical path latency. So therefore, we have evaluated critical path latency for these circuit blocks for various CMOS technology nodes using the scaling equations from literature. So the table shown here has the evaluated critical path latency values and the corresponding clock rates. So as you can infer from this table, the 14 nanometer SOI CMOS technology node achieves the highest clock rate. Therefore, heterogeneous integration of 45 nanometer or 34 nanometer silicon photonics technology node with 14 nanometer SOI CMOS node can be an excellent alternative for designing Ponalo to achieve high computation speeds. So the next performance metric we have evaluated is energy per bit. So we have energy per bit values for various configurations of Ponalo. So in total EPB for each configuration, we have added laser EPB, modulator and receiver EPB, dynamic EPB, and EPB related to leakage power. So as we can observe from this figure, for different Ponalo configurations, 64-bit Ponalo implemented from 45 nanometer SiP with 14 nanometer CMOS here, and 32 nanometer SiP with 14 nanometer CMOS achieve lowest EPB compared to other configurations. Therefore, heterogeneous integration of CMOS and SiP technology nodes for realizing PONALUs increases the energy efficiency of PONALU. So we have also analyzed optical loss for different configurations of PONALU. So we utilize the equation shown here in order to evaluate the maximum number of wavelengths we can accommodate per waveguide based on the power budget and total losses in the waveguide. So in this equation, we have maximum allowable optical power per waveguide and photodetector sensitivity, which is the minimum amount of signal power that can be detected at the receiver. So we also consider total losses in the waveguide, which are propagation loss, coupling loss, modulator and detector crosstalk and signal truncation penalties, which depend on the utilized silicon photonic technology node. So what we can infer from this equation is that for a given value of maximum permissible n lambda, which is n lambda p, total losses per waveguide should be within the budget. Now, using this equation, we have evaluated n lambda p values for 45 nanometer SOI CMOS and 32 nanometer SOI CMOS, which turned out to be 121 and 60. So we compare this n lambda p values with n lambda for various PONALU configurations based on different combinations of bit precision and number of waveguides which are provided in this table. So we also mark the configurations, PONALU configurations that render n lambda greater than n lambda p to be invalid. So from this analysis, the design guideline is that the scalability of PONALU in terms of WDM degree depends on the utilized silicon photonics technology node, and it can be improved for a specific technology node by reducing the optical losses rendered by that node. So the final performance metric we have evaluated is computing density. So we have evaluated computing density values for homogeneously integrated CMOS SiP nodes. So from these results, we can observe that 45 nanometer SiP with 45 nanometer CMOS node achieves better computing density. Since 45 nanometer SiP node has higher modulator speeds compared to 32 nanometer SiP node, even though it is clear that 45 nanometer SiP node with the 45 nanometer CMOS node achieves better computing density, but integrating larger SiP technology node with smallest available CMOS node for realizing PONALU yields higher efficiency and computing density, which is our final derived design guideline. So these are the conclusions from my work. Thank you.
Okay, thank you very much. Do we have some questions from the audience? Yes.
Yeah, you talked a lot about the speed. Can you maybe comment on whether the constant conversions between electronics, photonics, electronics constitute a speed bottleneck?
Was the question clear?
No, can you repeat it? I cannot hear it.
I'll try to summarize it. The question is, does the conversion between electronics, photonics represents a speed bottleneck in the system?
Yes, because the thing is, the silicon photonics devices, modulators especially, they have higher operating speeds compared to the CMOS technology nodes, the 45 nanometer, 32 nanometer. So there is clearly a difference in over there. So for CMOS, for silicon photonics technology nodes, the corresponding modulators for silicon photonics technology nodes, the operating speeds have been demonstrated up to 50 Gbps, whereas for CMOS technology nodes devices, they are not that faster. So clearly there is a difference over there. So I think that's my answer. That's why there's one of the design guidelines is that integrating smaller CMOS technology node with 45 nanometer silicon photonics technology node yields it has greater computing speeds compared to other heterogeneous integrations. So yeah.
Thank you. Is there any other question? No? Okay, then we can close. Thank you for the presentation. Thank you all for all the presenters in the session, and yeah. Okay, now we're going to continue with the work in progress papers, and that is the last small session for today. And I'm going to give the floor to Jeroen.
Because
Yeah, it's easier if you sit there. Okay, thanks, Philip. So now we arrive at the last session of today. This is the work in progress session. So we have 3 work in progress papers, which are short papers with shorter presentations. And the first one is by Philip Del Uña. Do I pronounce it correctly? And the title is On Demand Simul-Channel Impulse Response Shaping in Smart On-Chip Electromagnetic Environments. And Philip is a tenured CNRS researcher at the Institute of d'Électronique et de Technologie du Numérique in France. And he has a master's and PhD in physics from Imperial College London and Université Sorbonne in Paris, respectively. And during his PhD, he was also at Longeville in Paris. Finally, his research interests include engineering, the interaction of waves with metasurface programmable complex media for applications in wireless communication, intelligent imaging, and analog computing. So, Philip, the floor is yours. Feel free to start.
All right. So, hi everybody. Thanks for the introduction. So, in this talk, I'll cover some of our recent progress on making wireless networks on chips programmable. And so this is collaborative work with Mohamed Reza Imani from Arizona State University, Sergi Abadel, who's here with us from Polytechnical University in Catalonia, and myself, like you just heard, I'm based in Rennes in northwest France. So here's a quick outline of my talk, and because I have only 7 minutes, I'll cover all of this fairly quickly. So I'll start with the motivation for considering wireless networks on chips and the associated dilemma. Then I'll cover our recent introduction of the concept of programmable wireless networks on chips and a proposed implementation. And then finally, our work in progress towards making this concept more applicable to multiple receivers. So why are wireless networks on chips interesting? Essentially, as we integrate more and more processors into one chip, we need to think about communication between all of these processors. Currently, that is done mainly with wired interconnects, but that they have certain drawbacks in terms of loss and latency. And so the communication between different cores on the same chip is actually becoming a speed bottleneck. And that drives research in finding alternative or complementary interconnect solutions, and one of them are wireless links. They're interesting because they have this broadcast capability, they have an intrinsic system level flexibility, but they also have their own dilemma because they are limited to very simple modulation schemes like on-off keying. And so that means that given the particularities of the channels on chip, that creates problems because the chip is actually, if you carefully look at it, it's an enclosure, it's a metallic enclosure. And so you have a strong multipath, which means you have a lot of fading. And so essentially, depending on how you choose the different layers on your chip, either you have a good received signal strength, but a lot of multipath, or you have a very weak signal strength and no multipath. And you can see sort of here the range of channel impulse responses that you can get depending on how you choose the loss on your chip. But so neither of these is good, because if you have very weak signal, your communication is bad. But if you have very strong signal with a long impulse response and you have to do on-off keying, then also your transfer rate is very low. And so of course you can try to find a trade-off in terms of fixing the amount of loss. But actually what we've been proposing is to actually make this environment programmable and to thereby shape the channel impulse response. So here you can see, well, a prototypical chip design. So you have the different cores here. They're equipped with antennas that want to wirelessly communicate. Here's the metallic enclosure of the chip package. And so what we're proposing is to add a programmable metasurface on the ceiling that'll allow us to engineer the scattering properties of the wireless channels, and thereby to shape the channels in order to have pulse-like channel impulse responses despite the rich scattering. And so recently we started to look at one specific connection between one transmitter and one receiver. So here you can see the envelopes of the channel impulse responses if you just have random configurations of the programmable metasurface. And you can see that there's considerable amount of scattering and multipath, which would mean that if you have to do on-off keying, here you would have to have a very low data rate in order to avoid intersymbol interference. And then what we showed was that as you optimize the configuration of the programmable metasurface, you can actually impose on a specific targeted link, wireless link, that the channel impulse response is kind of pulse-like. And so you can drastically increase the data transmission rate. And so this was what we had done. And now the thing is, though, that if you think about wireless networks and chips, one of the attractive features is that you have this broadcast feature. So one antenna can simultaneously transmit to many receivers, many receiving cores. And so that's what we looked at here in this work in progress paper, that the scenario where we have one transmitter and multiple receivers that simultaneously receive. And so now we want to make sure that the channel impulse response from the transmitter to 3 different receivers, they're all as pulse-like as possible. So that, of course, becomes a multi-constraint optimization problem. Here's again, similar chip that we considered. We have 25 programmable meta atoms. This is our transmitter and the 3 receivers. And here you can see in red, again, the distributions of different channel impulse response envelopes for random configurations of the metasurface, and in black, the configuration that we identified as being optimal. And you can see, even though it's not perfect, it's a lot better than without the engineered environment. So with that, I'll wrap up. So we introduced this paradigm of programmable wireless networks and chips, which essentially allows us to overcome this RSSI-ISI dilemma by sort of doing an equalization over the air. And so we applied this concept in single input, single output, and then now we extended it to single input, multiple output. And the first 2 points, they're covered in our recent preprint. And now looking forward, we're actually implementing communication simulations of this on-off keying to actually see the impact of the channel impulse response on bit error rates and so on. With that, I'm happy to take any questions.
Thank you very much, Philip. Let's thank the speaker first. And maybe there are questions from the online audience. They have been a bit quiet lately. So if you have any question, please raise your hand. I see Jorge is raising his hand, so go ahead.
Thank you. Yes, we have been a little bit quiet. And thanks for the slides. Is there any preliminary results concerning the
Jorge, you're muted now.
Sorry. Is there any preliminary results concerning the bandwidth? You have exhibited the channel impulse response. That is, for that we can account for the interference between consecutive symbols. That is, if we have 2 peaks, then the first peak will interfere to the second one whenever we transmit a pulse from the emitter to the receiver. But what about bandwidth? Have you considered that?
I'm sorry, what is exactly the question? Have we considered the bandwidth of the transmission, of the modulation scheme?
Of the channel, not the modulation scheme, but from the channel. That is, okay. You have the channel input response in time, but in frequency?
Yeah, so, well, I mean, obviously these are just related to a Fourier transform. And so we actually conducted the full wave simulations in the frequency domain, and then we Fourier transformed it, well, inverse Fourier transformed it to see the temporal impulse response. So as you can see here, I didn't dwell on this too much, but we're looking at operating around 60 gigahertz with roughly 10 gigahertz bandwidth.
Oh, I see.
Does that answer your question?
Yes.
Okay.
Okay, thank you.
Other questions from the online audience or the live audience? Philip?
Yeah, I was always wondering in such kind of shielded environments or where you're trying to design the channel, like what is the effect of temperature change? Like, can you just ignore that or not?
Repeat the question.
So the question was if temperature changes might impact the channels, I guess.
Yes.
And so we haven't looked into this. I think potentially the temperature changes might change the dielectric properties of the different layers, and so they would impact the channels. In principle, though, because everything is programmable, we could find different configurations for different temperatures, and so adapt to changing temperatures, and thereby a sort of guarantee that we can have a pulse-like channel irrespective of the temperature by adapting the configuration to the temperature.
Well, it's kind of a chicken and egg problem, or not really. Because what as far as I understand, what you want to do is pre-characterize and then use the chip. But then you will have some kind of changes in temperature during the usage where you will not be able to pre-characterize it anymore. So you would have to kind of adjust on the fly. Would that be?
Well, you might have some temperature sensor or something, and then you could adapt to that. Or maybe, I mean, you can probably also look at you can maybe predict the temperature also based on what's going on the chip in terms of computations, or maybe look at the received signals and figure out, I mean, there might be different ways to infer the temperature.
Thank you.
Okay. Thank you, Philip. Let's thank him one more time. So yeah, that brings us to our second speaker for the session. So Hamid could come forward to set up. Yeah, you can just put it in there.
Yes.
So let me quickly introduce our speaker. So he is Hamid Kos-Feker Rutsari. His presentation is about cardiac bio-nano networks, extracellular matrix modeling for the propagation of extracellular vesicles. And Hamid received his Bachelor of Science degree in electrical engineering from the KN2C University of Technology in Tehran, and also a Master of Science degree in biomedical engineering from Tarbiyat Modares University, also in Tehran in 2020. And now he's pursuing a PhD degree in the Department of Clinical Medicine of the University of Oslo in Norway, in collaboration with the Oslo University Hospital. And his research interests are in the area of design and analysis of molecular communication-based networks and mathematical modeling of biological systems for intra-body system models. So Hamid, go ahead, the floor is yours.
Yeah, thank you so much. So I would like to present our paper as kind of a work in progress paper. So this work, the authors are myself, Dr. Mladen Velitic, and Dr.
Sorry to interrupt, but we need to unpause the screen sharing because people online cannot see it. Yes, now. Now you can, sorry to interrupt.
Yeah. So this work, the authors are myself, Dr. Mladen Velitic, Dr. Jakub Bergsdan, and Professor Ilan Kubalasinga. So the title of our work is Cardiac Bio-Nano Network Extracellular Matrix Modeling for the Propagation of Extracellular Vesicles. So first of all, I would like to talk a little about the extracellular vesicles or EVs. So these EVs are nano-sized vehicles of biomolecules, specifically genetic data such as RNA and DNA, and other types of biomolecules such as proteins and lipids, and they can be engineered to carry some nanoparticle drugs, which are very important for us. Another important and interesting thing about EVs is that they can be engineered for targeting specific types of cells, for example, cancer cells or other types of disorders, using engineering their membrane proteins. So in this work in progress paper, we used our recent EV release modeling based on therapeutic bio-nano machines. So one of the questions that I saw in this workshop was that what are exactly the bio-nano machines? So in our case, we are considering therapeutic bio-nano machines. So in our recent work, we considered the calcium signaling as a mediator of extracellular vesicle release. So this, we are saying that the change of concentration of calcium ions can lead to the release of EVs. So the thing is that if we could engineer the ionic channels of for example, the generic cells or synthetic cells that we are considering as human-induced pluripotent stem cell-derived cardiomyocytes. So if we could engineer the ionic channels, for example, transient receptor potential channels, so then we can control and change the cellular functions of the cells. So the question is how it is possible. So recently, the people in the field of nanotechnology are working on nanomaterial induced calcium influx, specifically from transient receptor potential channels. So in our lab, we are also working, we are having new projects and new people specifically from the field of biology to help us and for our aims actually. So there are different types of engineering the calcium channels for cardiomyocytes, for example, energy-based approaches, optical approaches. And another important thing is exposure to nanomaterials such as magnetic nanoparticles. So one of the important things is that are magnetic nanoparticles safe? Are they biocompatible or so on? The question is, yes, they can be safe using biological synthesis. For example, using plants, microorganisms, such as fungi, virus, and bacteria. So in our work, in this work in progress paper, we modeled the cardiac extracellular matrix, which is the propagation medium of these EVs for diffusion and propagation inside the cardiac tissue. So the cardiac extracellular matrix is actually a non-cellular compartment of cardiac tissue composed of filamentous proteins and mainly collagen, specifically collagen type 1 and type 3. So the cardiac ECM also is responsible for some cellular functions, for example, cell migration in the cardiac tissue, and also it has some responsibility for establishing architectural functions, for example, for proper cardiac function and cardiomyocyte contraction. So how we model the cardiac ECM for propagation of EVs? So we basically considered three main parameters such as tortuosity, volume fraction, and degradation of EVs. So one of the questions regarding the EVs is that how by the fact that the average mesh size of ECM is smaller than the average diameter of EVs, how it is possible for EVs to propagate through cardiac ECM? So the answer is in the fact that the cardiac ECM has some specific stress relaxation, as well as water transport through kind of specific proteins such as acoprotein 1, so these EVs can deform and reshape and diffuse through cardiac ECM. Another important parameter that we considered is volume fraction, which is the accessible volume for propagation of EVs compared to whole cardiac tissue. Another important thing is degradation of EVs through their natural half-life, which is basically based on three important parameters: that the location that they have been administered, the type of cells that they are originated from, and the availability of the target cells for their internalization and their uptake. So to model the EV propagation, we considered the general convection advection PDE or partial differential equation problem, which has the three main parts for diffusion, bulk flow of ECM, and also source of sink, which we consider the degradation of EVs. So this PDE has two boundary condition as, so the one says that the change of concentration of EVs is equals, it has a relation with the EV release rate, which we considered from our recent work. And another boundary condition says that the change of EV's concentration equals to 0, at the right boundary condition, and also for the initial condition, we're saying that the initial value of concentration is 0. So this complex PDE needs to be simplified actually for this work in progress paper, but in our future works, we consider the more complex system for the propagation of EVs. So in this work, we simplified it using radial symmetry. As part of the result, so we consider 2 EV release rate, as we can see here, based on 2 control signal, which we are considering them from the external device. And so with two heart rates as 80 beat per minute and 120 beat per minute. And here we can see the EV concentration dynamics by considering 0 bulk flow and 5 micrometer per second bulk flow. And here, for example, we can see the line, the diagonal line, which shows the bulk flow. And for example, here also we can see these lines, which are because of the peaks of, at the EV release rate. So as part of the conclusion, so in this work in progress paper, we modeled the propagation of extrasolar vesicles through cardiac extrasolar matrix. And for the aim of targeted direct delivery for future healthcare systems, specifically for cardiovascular disease. And we used our recent works on modulation of EVs for EV release. And also we simplified it using radial symmetry. Thank you so much for your attention, and I will be happy to answer your questions.
Thank you, Hamid. Let's thank the speaker. Any questions, either from the live audience or online? Okay, let me ask you something. I don't know if you mentioned it now, but in the paper you talked about validating these results with the data-driven models.
Yes.
And I was wondering how do you go about collecting real data that can be used for such a thing?
Yes. So I can show maybe this slide. So we are working actually on 2 projects for experimental results. First is modeling the intracellular calcium signaling in cardiomyocytes using calcium imaging for cardiomyocytes. And another work is manipulation of ionic channels and manipulation and control of intracellular calcium levels using magnetic nanoparticle. So we use magnetic nanoparticle to kind of control the calcium levels. And then by using magnetic field from outside of the cell. So here will be some, the cells will be on the dish, not in the body. So at the preliminary, so we could have some preliminary result. And then with magnetic magnetic field, you can control the opening and closing of ionic channels. So then you can control the calcium levels of the in the cardiomyocytes, and then maybe control the release of EVs for therapeutic applications.
So the experiments are not with live test subjects, but with harvested cells.
Yes, they are in vitro, I think.
Yeah.
Yeah.
Okay. Thank you.
Yeah.
If there are any other questions, now is your chance. Otherwise, let's thank Hamid again.
Thank you.
And then we have our last speaker for today. Her name is Francesca Ratti. So Francesca is online, so you can go ahead and start sharing your screen while I introduce you. So she's a PhD candidate in information technology at the Politecnico di Milano in Italy. She obtained a master's degree with honors in telecommunication engineering in 2018 from the same university, with a thesis on the topic of information exchange in molecular communications. So her research interests are in the communication and information theory applied to biology, on topics such as molecular communication, system biology, and synthetic biology. So Francesca, I see you're sharing your screen already, so feel free to start your presentation.
Perfect. Thank you for the introduction. So good morning, I am Francesca. I'm a PhD student in information technology, and today I'm presenting this work in progress paper with my co-authors that are Maurizio Magarini, that is a professor in information theory and digital communication at Politecnico di Milano. This is my home university. And I'm Dana Wan, that is a researcher at the Walton Institute for Information and Communication System Science in Waterford, Ireland. Okay. Among the concepts that have been explored in the areas of systems and synthetic biology, a key phenomenon is that of retroactivity. Retroactivity is the back action from a downstream system connected to an upstream one, which is observed in biomolecular systems. Differently from feedback, its effect cannot be removed. This back action, this back propagated signal generated by the interconnected components has a non-negligible impact not only in the design of biomolecular circuits, but also in the communication performance of the upstream system. The objective in this work is to achieve the mitigation of retroactivity by introducing a retroactivity suppressor in the system and study its impact on the communication properties of the system itself. The motivation behind this objective is to present a new solution to counter the loading effects from downstream systems, so the retroactivity, which modifies the dynamics of the upstream system. We consider the signaling circuit model in the figure on the left. The primary system is composed by a single-step enzymatic reaction where A and B are the input and the output protein of the system. This enzymatic reaction can be seen as a communication system in which the transmitted message is A and the corresponding received one is B. The so-called downstream system models the binding of the output B with Q to form R. For example, Q can be the free DNA to which the protein B connects and generates the complex R. The binding of B with Q represents a peculiarity of communication in biological systems. In fact, here, during the process of transmission through the communication system, the message is consumed, so meaning that the molecules are sequestrated by the receiver. The mitigation of the impact of retroactivity on the communication performance between A and B is performed by adding a secondary upstream system that we named retroactivity suppressor that connects to the downstream system in place of B. Once again, it consists of a single-step enzymatic reaction analogous to the one describing the primary system, and with the peculiarity that its output G connects with the same pool of free Q, so basically subtracting free Q from the environment. Since in this paper we adopted a simulation-based approach, we built the described biomolecular circuit in MATLAB SimBiology, as shown in the figure on the right. Without the presence of any downstream systems, after some time, all the A present in the system transforms into B. Therefore, at steady state, we would expect A equal to 0 nanomoles. So by supposing that the injected value of A represents a symbol to be transmitted and the corresponding value of B at steady state, the received one, we would get a sort of perfect communication system. The presence of the downstream system subtracts free B to the environment. So at steady state, we find less B in the system with respect to the ideal case. This could lead to a misinterpretation of the transmitted symbol. And these figures depict the value of each species present in the system as a function of time. Supposing of injecting a quantity of 1.5 by 10 to the power of 4 nanomoles of A after 1 minute from the starting of the simulation. Clearly, we inject the same amount of F when the retroactivity suppressor module is present. It is possible to note that the value of free B for the model without retroactivity suppressor saturates almost at 0 nanomoles. Instead, when we add the retroactivity suppressor system, the value of 3b keeps increasing with time until it saturates around 7.5 by 10 to the power of 3 nanomoles. So although not all the produced B is free, at steady state, its value is much greater than without the presence of the retroactivity suppressor. This leads to the mitigation of retroactivity and consequently to a higher communication performance, as the value of 3b is closer to the one in the ideal case. In these figures, we consider B as a function of A. We perform 3 stochastic simulations to take into account of the randomness introduced by the chemical reactions. And both A and B start at 0 nanomoles. And then when the amount of A is injected in the system, B starts increasing as A consumes. While in the case of presence of retroactivity suppressor, the value of 3b saturates around 7.5 by 10 to the power of 3 nanomoles, as we saw in the previous slide. When A is completely consumed, if we do not implement the retroactivity suppressor, the value of 3b goes to 0. So in this work, we showed very preliminary results on the mitigation of the impact of retroactivity on communication performance in biomolecular circuits. I want to remark that the effect of retroactivity is present in all biological communication systems that can be composed of a cascade of reactions that can be seen as a cascade of systems. For future work, we plan to generalize our approach by building an analytical formalization rather than a simulation-based approach of the proposed solution to suppress the retroactivity effect on the communication performance. And now I'm open to any questions if there are.
Thank you, Francesca. Let's thank the speaker. Any questions? Any questions online? Yeah, Jorge?
Yes, really interesting work. I only have, out of curiosity, one question. Because if I understood correctly, that is, you are introducing such an artificial system just to cancel out some retroactive signal that it is produced because of a natural process, let's say.
Yes.
Then may I ask then if this retroactive suppressor, it must be synchronized with the emitter. That is, this retroactive processor may produce this new component, but because it is not aligned with the transmitter, then you're introducing much more noise in the channel because you want to suppress something that is not there. Might be that the case?
Yes, this is totally a possibility. Clearly now this was a very simplified setup, I would say, in which we were supposing that the retroactivity suppressor was producing some compound only when also the primary system was active. So basically it was balancing the effect of retroactivity, but being active only when the primary system was active and the downstream system was active too. So yes, this was an hypothesis that we made, just because it's a very preliminary work, I have to say, but yes.
Okay. Even though it is a really good work. Thank you.
Okay, thank you very much. In the interest of time, I think we'll leave it at this one question. So thank you again, Francesca, and thank you all the speakers in this session. So let's thank all of them one last time. And yeah, that brings us to the final part of the workshop. So I'll leave the floor to Philippe to wrap up.
The slides.
The slides, they are here. I think here, yeah.
Works. Can you hear me? Okay, this is only gonna take a second or two. This is just to give the best paper award and the best work in progress paper and best paper award. Before I go into that, I would like to thank our TPC. You can see the list here. They did an amazing job. Each of them evaluated roughly 2 papers, and each paper got generally 3 or more reviews. And then later on, the organizing committee, the colleagues of mine, they and me, we assessed the quality of the reviews, and we assessed also the scores, and we generally agree. So the papers that got the high scores by the reviewers were the ones that eventually got the best paper award. And what's this? So the best work in progress paper award goes to Hamid Kosferi, Rudari, Mladen Veletic, Jakob Bergsland, and Ilanko Balasingham for the work in progress paper entitled Cardiac Bionano Network, Extracellular Matrix Modeling for the Propagation of Extracellular Vesicle. So yeah, congratulations. The award is only in the digital format due to COVID restrictions. And then the best paper award goes to Jorge Torres Gomez, Anke Kustner, Ketki Pitke, Jennifer Simonian, Bige Denise Unluturk, and Falco Dresler for the paper entitled The Machine Learning Approach for Abnormality Detection in Blood Vessels via Mobile Nanosensors.
Thank you very much. We are really, in behalf of the author, we are really thankful for this result. Thank you to the organizers. Nice to be here.
Yeah, thank you. Yeah, congratulations to the awardees, and thank you all for contributing, for being present here, for providing your talks. It was a pleasure to have you, and see you next year. Bye.
Bye-bye.